We are taught to think of space as a giant empty room with a few scattered lights. But the more humans have stared at the sky, the more it has behaved like a trick mirror, quietly breaking our sense of what big even means. For a long time, even expert scientists were sure our own galaxy was almost everything there was. Then the sky proved them wrong, again and again. In this video, we'll slow down together and look more closely at one nearby galaxy and learn what big really is out there. If you like drifting off while thinking about gentle, strange science, I'd really appreciate it if you tap like and subscribe. It helps other people find this video too and get good sleep while learning, and it means a lot to me. Wherever you are right now, there is a sky above you. It might be hidden by a ceiling and a roof. It might be peeking in through a window. It might be stretching openly above you if you are outside, but it is there, the same sky that has been over every person who has ever lived. High in that sky, there is a quiet neighbor. Not a bright star that shouts for attention. Not a wandering planet that creeps across the zodiac. Something softer, a whole galaxy that from here pretends to be almost nothing at all. If your night is dark enough, and if you know just where to let your eyes rest, you can see it with no tools at all. It does not look like the dramatic photographs you may have seen. It appears as the faintest smudge. A small, pale thumbprint of light just off the constellation of Andromeda. No sparkle. No color. Just a blur that many people walk under for their entire lives without ever noticing. It almost feels shy, as if it is waiting for the people who are willing to slow down. The ones who will let their eyes adjust, who will stare a little longer than is strictly necessary. When you do that, you are quietly joining a line of watchers that goes back for thousands of years. People who had no idea what it really was, but still felt there was something odd about that little cloud in the sky. As you listen, you might be lying in bed, already wrapped in blankets. You might be in a chair, letting the day finally drift away. Maybe it is early evening where you are, with a bit of blue still left outside. Maybe it is deep night, the hour when even busy cities begin to fall quiet. Above all of that, the same sky stretches on. Your weather might be cloudy. Someone else's sky might be perfectly clear. On one side of the world, the sun may already be rising. On another, the moon might be high. But Andromeda hangs there for all of us, whether we can see it tonight or not. The light from that faint blur began its journey before any human wrote anything down, before alphabets. Before stories lived on paper, long before anyone could have imagined words like galaxy or universe. That light has been crossing space all that time, and tonight a tiny part of it happens to arrive while you are here, listening, breathing, getting ready to sleep. The strange thing is that Andromeda can feel familiar and completely unknown at the same time. You may have seen it in pictures, a neat spiral, a glowing center, long, misty arms curling outward. It is one of the most photographed galaxies in the sky. We draw it, we label it, we put it in diagrams as if it were a simple object you could point at on a shelf. But the more you think about what it really is, the more it slips out of your hands. When we use the word galaxy, we are not talking about one thing. We are talking about a vast crowd, hundreds of billions of stars, clouds of gas, bigger than anything we can picture. Fine dust spread through space like smoke. And on top of all of that, a deep sea of invisible matter that we cannot see, but that pulls on everything with its gravity. In the middle sits a heavy, restless heart, where that gravity folds space around it. Andromeda has all of this, and more. It is not just a pretty spiral drawn in light. It is a system, a city of stars on a scale so large that even our biggest words feel small when we try to use them. If your eyes were sensitive enough to catch every trace of its glow, Andromeda would stretch across the sky many times wider than the full moon. It would be a great pale whirlpool hanging above you. But our eyes are modest. They only pick up the brightest part near the center. The rest is there, but too soft for our night vision. Telescopes and long camera exposures do the work our eyes cannot, gathering those faint photons and turning them into the sweeping shapes you see in images. So when we ask, how big is Andromeda? The question is trickier than it sounds. What are we actually trying to measure? We could talk about its width, the distance from one outer edge of a spiral arm to the opposite edge. We could talk about how many stars it holds, each star with its own size, its own planets, its own possible stories. We could talk about the invisible weight of the matter we cannot see that wraps around it and holds it together, or we could talk about its importance to us. It is the closest big spiral galaxy to our own, a neighbor so close, in cosmic terms, that its future is already linked with the future of the Milky Way through gravity. For a galaxy like Andromeda, big is not just a number, it is a shift in perspective. If you close your eyes for a moment and think of the word big, your mind probably pulls out familiar images. Maybe a mountain range rising against the horizon. Maybe the flat, endless surface of an ocean. Maybe a city skyline, full of buildings stacked like glass cliffs. Maybe even the whole Earth as seen from space. A round, cloud-wrapped ball. All of those feel enormous to us. They are enormous to us. But Andromeda is larger than any of them can hint at, larger than any single comparison can really hold. It is not big in the way that one building is taller than another building. It is big in the way that a whole world is bigger than a single room. It contains multitudes, billions of suns. Clouds and structures that would swallow our entire solar system without noticing. Trying to hold that in one thought is hard. The mind keeps wanting to shrink it back to something familiar. And that is exactly where our exploration begins. Picture yourself far from cities, under a sky that is actually dark, no street lamps, no glow from distant buildings, just the night and a wide horizon. The longer you look up, the more stars appear. They stop being a handful of bright points and start to feel like dust scattered across black glass. Somewhere above that horizon, the faint oval of Andromeda hangs. It does not look like a star. Stars are sharp and tiny. It does not look like a planet. Planets are steady and bright. Andromeda is softer. A small, ghost-like haze that seems almost out of focus. If you know what you are looking at, there is a strange shift. That blur is not one thing. It is the combined light of hundreds of billions of distant suns, all smeared together by distance until they blend into a single pale patch on your retina. Your eyes are only catching the tiniest piece of what is really there. That blur is also far away. The light falling into your eyes has traveled for around 2.5 million years. In that time, whole species have appeared and vanished on Earth. Ice ages have come and gone. Forests have grown, burned, and grown again. Human beings have learned to speak, to farm, to build cities, to launch telescopes into space, all while this one stream of light kept going. And yet, in the vastness of the universe, this distance is considered close. Andromeda and our Milky Way live in the same little cosmic neighborhood, drifting together in a small collection of galaxies. That nearness is one reason we can see it at all. Most galaxies are so far away that their light never climbs above the threshold of our seeing. Even so, what our eyes show us is only the crowded center. Around that bright core, invisible without help, great arms curve outward on both sides. In those arms, younger stars burn, blue and hot. Pockets of gas glow where new stars are being born. Long bands of dust snake through, cutting dark lanes across the starlight like shadows in a fog. If our eyes could see in other kinds of light, Andromeda would appear even more intricate. In ultraviolet, the youngest stars would flare out, marking fresh star birth, like sparks along the arms. In infrared, we would see the warmth of dust and gas, stretching much farther than the bright center suggests. The simple word galaxy does not really prepare us for all of that hidden structure, but from the ground, on a normal night, none of this is obvious. There is only the blur and the knowledge behind it, a question hanging in the darkness. How big is it really? That is what we are going to explore together. Not with a rush of facts, not with a storm of numbers. We will move slowly. We will give your mind time to picture each step. There will be room for wonder, and room for quiet, and room to let the thoughts drift and soften as you rest. Because even though we are going to talk about something as huge as a galaxy, the aim here is still gentle. It is still sleep. If you step outside on a dark enough night and give your eyes a little time, you can do something that sounds almost impossible. You can meet a whole galaxy with nothing but your own vision. Most galaxies are far too faint for that. Their light is spread so thinly across space that by the time it reaches us, it has faded below what our eyes can notice. They are there, filling the universe, but they stay hidden unless you use powerful instruments. Andromeda is one of the rare exceptions. It is close enough and bright enough that a human standing under the right sky can see it as a tiny ghost of light. No telescope, no camera, just you and the night. That puts Andromeda in a very small club. It is not just an object on a scientist's screen. It is a neighbor in the sky that any person, in any century, could have met. Our ancestors did not know it was a galaxy. They did not have that word yet. But they knew there was a little blur there that did not behave like the others. For most of human history, the night sky was not something distant. It was as familiar as the landscape. People slept under it, worked beneath it, planned their lives by it. Farmers watched how certain stars rose and set to decide when to plant and harvest. Sailors steered ships by patterns that hung over the ocean. Storytellers used the sky as a giant canvas, drawing figures in the stars and filling them with heroes, monsters, and lessons. Somewhere inside that web of stories sat Andromeda. Not as a spiral galaxy, just as a faint, curious patch of light near the stars that formed the figure of a chained princess in Greek myth. Different cultures gave different names and meanings, but many of them noticed the same small strangeness. It was softer than a star. It did not have the clear disk of a planet. It was something in between. Something that hinted at being larger than its appearance allowed. If you wanted to try to find it yourself, you could follow the same sky that guided them. You would start with Pegasus, the flying horse. Look for a big, almost perfect square of bright stars. That square is one of the easiest shapes to spot on an autumn night in the northern hemisphere. From there, you trace a line of stars that marks the figure of Andromeda, the princess. Along that line, a little off to the side, lies the faint oval glow. To the unaided eye, it will not look spectacular, just a soft smudge that is easy to miss if you are not expecting it. If you bring binoculars to your eyes, the smudge stretches out, more like a thin, glowing almond. With a small telescope, structure begins to appear. You start to see a brighter center and a flattened disk around it. With larger instruments and long exposure photography, the full spiral shape slowly reveals itself. Arms, dust lanes, knots of stars. The little blur becomes a swirling system. No matter how you look at it, though, the same basic fact holds. That pale patch is an entire galaxy, more than twice the size of our own Milky Way, seen from across millions of light years. The photons that reach your eyes tonight left Andromeda about 2.5 million years ago. Back then, early humans on Earth were using stone tools. There were no cities, no written language, no one who could even imagine that somewhere in the night there were other galaxies. So the Andromeda you see is not the Andromeda that exists right now. It is the Andromeda of long ago. In a very literal way, you are looking back in time. Every time you glance up and find that blur, another batch of ancient light finally arrives and ends its journey in your eyes. Astronomers talk about this a lot. Light is not just illumination, it is a record. It carries the history of where it came from. Andromeda is close enough for us to see, but far enough that its light comes from a chapter of its story that began before human history. That mix of closeness and distance makes it feel even bigger. Not only in size, but in time. You might notice that your mind reacts differently to that idea than it does to a simple number. 2.5 million light-years is a phrase that can slide past without quite landing, but picturing early humans with stone tools under the same sky you stand beneath now, while light from Andromeda was already on its way, turns the distance into something you can feel. It becomes a meeting between your scale and the galaxy's scale. When you imagine Andromeda as it really is, that feeling deepens. The part you can see with your eyes is just the crowded central bulge, where stars are packed tightly together. Around that bulge, the galaxy spreads out far beyond the blur. Its disk is huge. If all of it shone as brightly as the center, it would cover a patch of sky several times wider than the full moon. You would look up and see a giant spiral stretching across the heavens, arms thrown wide, as if it were wrapping the dome of the sky. Instead, our vision gathers only the brightest core. The rest is too faint, too spread out, for our eyes to register. Meeting Andromeda this way is a bit like meeting someone in very dim light. You can see their outline. You know there is a whole person there. You might even sense something of their posture, their presence. But the details of their face remain hidden until you bring in more light. Binoculars add a little more light. Telescopes add much more. Long exposures add even more, stacking photon upon photon over many minutes or hours. In those deeper views, colors appear, pale blue regions where young, hot stars shine. Softer yellow in the crowded central bulge where older stars gather, dark bands where dust blocks starlight. Faint tendrils where the spiral arms thin out into the space between galaxies. Each way of looking reveals another layer, yet the simplest way, the human eye on a clear night, still carries a special weight, because that is the one that links you directly to every wondered about that blur. No glass, no electronics, just your retina catching the same kind of photons that touched the eyes of shepherds, sailors and scholars. Across centuries, you can imagine them. Ancient Greek observers lying on stone rooftops, Persian and Arabic astronomers carefully mapping the stars. In the 10th century, Abd al-Rahman al-Sufi, writing about a little cloud in his book of fixed stars, giving a quiet, written home to that strange patch. Centuries later, European observers adding it to catalogues as a nebula, assuming it was just a small cloud of stars or gas within the Milky Way. None of them knew they were looking at a separate galaxy. The idea that there could be other island universes beyond our own was radical, and many believed the Milky Way was all there was. It took the careful work of Edwin Hubble in the early 20th century, using a large telescope and special variable stars as distance markers, to show that this blur was far beyond our galaxy. His measurements revealed that Andromeda was its own vast system, much larger than anyone had assumed. With that, the universe expanded in a single human lifetime. What had been everything became just one galaxy among many. Andromeda turned from a cloud in our backyard into our nearest great neighbor, across a cosmic sea. The sky that had seemed complete, filled with countless other galaxies. So when you stand outside and find that faint patch, now you are not just checking a box on a star map. You are standing in a line of human curiosity that runs through all those people. The same object sparked their questions and now sparks yours. The same photons that once fell on their eyes are replaced by new ones falling on yours. The story continued, and you stepped into it. Andromeda itself is not just a distant decoration in that story. It is physically tied to us. Our galaxy and Andromeda are bound together by gravity. They are moving toward each other, slowly, over billions of years. The smudge you see tonight is also a signpost of where our Milky Way is heading in the long run. The two galaxies are already caught in a slow-motion dance that will eventually bring them together. When we ask, how big is Andromeda, it helps to remember all of this. Size is not just a number written on a chart. It is how far its presence reaches into our sky. It is how far its light has traveled to meet our eyes. It is how deeply it sits in our history and our future. It is how it can be both barely visible and unimaginably large at the same time. Because that is another part of its strangeness. The real Andromeda stretches about 220,000 light-years across. It holds nearly 1 trillion stars, yet the part you see arrives as a fragile shimmer, barely brighter than the faintest stars around it. Immense reality, humble appearance. That contrast is part of why it stays in the mind once you have seen it. The first meeting is simple, just a blur in the dark, but if you let your thoughts wander, questions begin to unfold from that blur. What are those stars actually like? How far out do those hidden arms go? How do we even measure the distance to something so far away? How many solar systems move inside it? How many worlds might circle its suns? Each of those questions pulls you a little deeper. From the small patch of light your eyes can catch, into structures and scales that stretch far beyond anything we live with day to day, and as you drift towards sleep, you do not have to answer them. It is enough to feel that they are there. That from one quiet blur in the sky, a whole universe of mysteries opens. When people hear the words Andromeda Galaxy, it often feels like something that belongs far away from ordinary life. It sounds like a label from a textbook, or a caption under a photograph, or a distant swirl on a telescope poster. It can sit in your mind as an idea, but not as something you have actually met. But there is another version of Andromeda, the one that lives in the actual sky above you, the one your own eyes can touch. Some nights, if the air is clear and the lights are few, that version appears as a soft oval above the horizon, not bright, not dramatic, just a small, pale patch of light that is so modest most people never notice it at all. It sits there quietly while cars go by and windows glow and conversations happen underneath it, and all the while, your eyes are physically capable of gathering its light. Light that has traveled 2.5 million years through space, ending in the back of your eye without you even knowing. For a lot of people, Andromeda is something they have heard about, but never actually looked for. You might have stood outside at night and picked out the usual landmarks in the sky. The ones everybody learns first. The straight line of Orion's belt. The scoop of the Big Dipper. The bent W of Cassiopeia. These constellations grab your attention because they are obvious and bright and easy to outline with your finger. Andromeda does not behave like that. Its glow is quieter. It does not shout for attention. It does not pierce the darkness like a bright star. It just waits. It asks you to make the first move. You have to decide to look for it, and then, strangely, you do not even look directly at it. Stargazers have learned that if you stare straight at that faint patch, it sometimes disappears. Your eye is less sensitive in the very center of its vision. So instead, you look a little to the side. You use the edges of your vision, where your eyes are better at noticing faint light. This little trick has a name among observers. They call it averted vision. But in practice, it is very simple. You just soften your gaze and look slightly away from the thing you want to see. People have been using this trick for centuries without thinking much about the biology behind it. Just humans standing in the dark, letting their eyes adjust, letting the sky come to them. And then, at some point, there is a small change. A smudge appears where there was nothing. It is not dramatic. It is not like a firework or a flash. It is gentle, almost shy. A faint blur, an oval patch, nothing more. If you did not know what it was, you might shrug and move on. But if you do know, the entire feeling of that moment changes, because you are not just looking at a cloud. You are not just seeing some random mist. You are seeing the blended light of hundreds of billions of stars. Not a handful, not thousands. More stars than you could count in 1,000 lifetimes, all poured together into one dim shimmer that your eye can barely hold. When that fact lands, people often describe a very particular mix of feelings. Part of it is humility. You realize how small your own field of vision is, how much you normally do not see, how your eyes, which are perfect for reading a book or recognizing a friend's face, are tiny instruments when they are asked to hold a galaxy. You feel the limits of being human, but right next to that humility comes wonder. Because even with those limits, even with small eyes and a small body standing on a small planet, you are still managing to connect to something enormous. No spacecraft, no giant observatory, no complicated equations. Just you, the dark, and a little patch of sky. That simplicity is one of the quiet miracles of Andromeda. It is not locked behind expensive equipment. It is not reserved for professionals. It is available to anyone who is willing to step outside and wait. If you have never done that, you can still try it in your imagination. Picture yourself somewhere far from the orange glow of city lights. Maybe you are standing in a field where the grass reaches your ankles. Maybe you are beside a still lake that holds the reflections of the stars. Maybe you are on a mountain where the air is cooler and thinner and every sound seems sharper. You look up and the sky looks different from the one you see at home. The stars are not just a handful of points breaking through the haze. They are everywhere. The Milky Way appears as a soft river of light, stretching from one side of the sky to the other, made of too many stars to separate. It feels like someone has painted a pale band across the darkness. Near that band, in the region we call the constellation Andromeda, something catches your attention. At first, you are not even sure why. It is not a point. It is not sharp. It is more like a fingerprint pressed gently on glass. A small oval smudge, pale, delicate, easy to miss if you were not looking for anything at all. But you stop. You let your eyes rest on the space beside it. You give them a minute to adjust. Slowly, quietly, the patch becomes more certain. Less like a trick of your vision, more like a real thing. There is a moment where a thought clicks in your mind, and it is simple. That's it. That's Andromeda. That is another galaxy. You might even say it to yourself in a whisper, and then another thought follows. The light that is touching my eyes right now began its journey before modern humans existed. Early humans were still shaping stone tools when those photons started out, and now they are ending their journey here, with you in this particular night. Many people say that seeing Andromeda in a photograph is impressive, but seeing it with their own eyes feels entirely different. A photograph can show more detail. It can stretch exposure times. It can reveal blues and golds and delicate dust lanes that human eyes cannot detect in real time. It can sharpen the spiral shape and outline the arms. But a photograph is always one step removed. It is captured, processed, displayed on a screen or on paper. It is something you look at, not something you share a moment with. Looking at Andromeda with your own eyes is about connection, not detail. You are standing under the same sky where ancient astronomers once stood. They had no telescopes at all. No cameras, only careful eyes and deep patience. You are under the same sky that guided travelers across oceans and deserts, using stars as silent markers. The same sky that has hung above countless people over thousands of years who tilted their heads back and saw that faint blur and wondered what it might be. In that instant, you become part of that long line. You join a chain of observers that stretches far behind you into history. No one else can see that moment from inside your mind, but you are continuing something humans have been doing for as long as we have been able to look up. It can be surprising and a little sad to realize how many people live their whole lives without knowing they can see another galaxy with nothing but their eyes. Modern life has thinned the sky for most of us. Streetlights flood the night with artificial day. Windows glow, billboards shine, tall buildings block the horizon. Air above cities swirls with haze and pollution. Under that kind of sky, only a few stars manage to break through. The brightest ones survive. The rest disappear behind the glow. The quiet things, like Andromeda, vanish first. And yet, The galaxy itself has not gone anywhere. It still hangs where it always has. Its light still pours down on the rooftops and highways and sidewalks every clear night. Photons from its stars still fall onto the tops of buses and into empty parking lots and through bedroom windows. They still slip through the atmosphere and land on our eyes, even if we cannot see them because the background is too bright. To stop and deliberately look for Andromeda in a place where the sky is dark enough is a way of reclaiming something old and gentle that the modern world has almost hidden. People who have had that experience often describe it in very personal ways. Some say they felt smaller, but in a relieving way, as if the tight circle of their daily problems expanded a little and became less heavy. Worries about work, about schedules, about little annoyances suddenly looked like tiny specks against the scale of galaxies. The weight of having to be important all the time lifted for a moment. Others say the opposite feeling rises at the same time. They feel more connected, not less. They feel like they are part of a larger pattern. Part of a universe that is not static, but alive with motion and light. Their own existence becomes one thin thread, woven into a tapestry that stretches far beyond any one life. That does not erase personal meaning. It gives it a backdrop. Some people say it makes them feel strangely grounded. That might sound odd at first. You are looking at something unimaginably far away, and somehow you feel more rooted where you stand. But distance can do that. When you understand that you are standing on a small world, in a small neighborhood of stars, inside a galaxy, staring at another galaxy, your place becomes clearer. You know where you are in the story, even if the story is enormous. It is also helpful to remember that the light from Andromeda does not arrive in one single burst. It is not like a message sent once and then finished. Every second, fresh packets of light start and finish their journey. New photons leave those distant stars, cross the emptiness, and reach us. So whenever you look up, you are meeting a new group of travelers. The light that reached your eyes yesterday is gone, absorbed and turned into tiny nerve signals. Tonight's light is different, though it began in the same galaxy, in roughly the same age. All of it is ancient, but it is also continuous. That means seeing Andromeda is not a one-time event. It is not like visiting a monument and checking it off a list. It is more like saying hello each time you cross paths with an old friend. The relationship is ongoing, even if you only notice it once in a while. The galaxy keeps sending. The Earth keeps moving. The light keeps arriving, pouring down whether we pay attention or not. Maybe you're listening to this in a city where the sky never really gets dark, where the horizon glows grey or orange, and only a few bright stars manage to pierce the haze. Maybe you have never seen Andromeda at all, and you are not sure you ever will. That is okay. The fact that you cannot see it from where you are does not change the fact that it is there. Hidden is not the same as gone. The limitation is local. It belongs to the lamps and the buildings and the weather of Earth, not to the galaxy itself. If, someday, you find yourself traveling to a place where the night is darker, you can carry this thought with you. Maybe you are on holiday in the countryside. Maybe you are camping. Maybe you step outside a small town late at night when most lights are off if you remember. You can give yourself a few minutes. Walk a little away from the brightest lamps. Let your eyes slowly adjust. Look up. Try to find that modest blur. It might take several tries. It might not cooperate the first time, but if you do catch it, even for a second, the reward is out of proportion to the effort. Astronomers can describe Andromeda with numbers. They will say that the main disk is about 220,000 light-years across. They will say it may contain close to 1 trillion stars. They will say it is moving toward us at around 110 kilometers each second. All of that is true. All of it matters for science. It lets us compare galaxies, test theories, build models, but none of those numbers can fully describe the feeling of simply standing under the sky and seeing that pale oval with your own vision. A measurement cannot recreate the quiet shock of realizing, that's another galaxy. I'm seeing another galaxy. No equation can capture the way your chest feels for a moment. You do not need to know how to calculate a light year to feel that. You do not need a degree. The encounter belongs to anyone with eyes and curiosity. It is one of the most democratic experiences the universe offers. That is why the simple question, have you ever seen Andromeda yourself, carries more weight than it seems at first. If you have, you know the small thrill, the gentle click of recognition. You may remember the surprise of how dim it looked and how enormous it actually is. You may remember the strange mix of that's all and that's everything happening at the same time. If you have not, then the idea of seeing it can sit in your mind as a kind of small adventure, not a dramatic expedition, just a quiet goal tucked away in your thoughts. One day, under the right sky, you might look for it. Knowing it is possible changes the way you think about the night. The sky becomes not just a backdrop, but a place with destinations you can visit without moving your feet. There is something deeply steadying in realizing that the world is full of wonders you can meet directly, not through screens, not through streaming, or images or filters, just by being there and looking up. Among all those direct wonders, the Andromeda Galaxy is one of the grandest. It is not just another star. It is not just another nebula. It is a whole neighboring galaxy, and your eyes are enough to reach it. To stand under it, searching for that faint blur, is to step outside your usual scale for a few minutes. You leave the scale of rooms and roads and calendars and step into the scale of galaxies. You do not suddenly understand everything. The details remain hidden. The spiral arms do not pop into focus, but the sense of size, of depth, of something far beyond your normal frame becomes very real. From the outside, nothing special seems to be happening. If someone walked past you while you were craning your neck and squinting at the sky, they might not even glance upward. They might assume you are just daydreaming at the stars. They would not see the thoughts in your head or the shift in your perspective. To them, it would look ordinary. Inside you, though, something rare is taking place. You are linking your little moment in time with a vast structure, millions of light years away. You are letting your mind stretch across both distance and history, joining early humans, medieval astronomers, and modern observers in a single quiet act, noticing a small blur and choosing to care what it is. That connection does not show on your face, but it is real. It turns what seemed like a meaningless smudge into a meeting. So the question circles back once more. Have you ever seen it with your own eyes? Have you ever stood under the stars and picked out that pale oval glow? If you have, you may remember the specifics. Maybe the air was cold enough that you could see your breath. Maybe crickets were chirping nearby. Maybe someone was standing beside you, and you nudged them and pointed and shared the discovery. Maybe it was quiet, and you were alone, and that felt right. If you have not, then the next time you find yourself under a truly dark sky, you can bring this memory of a thing you have not yet seen. You can remember that there is a neighbor galaxy hanging there, waiting to be noticed. When the moment comes and you finally find it, you will know that what you are seeing is not just a smudge. It is the closest great spiral galaxy to our own. It is a neighbor that is slowly moving toward us, locked into a long, graceful gravitational dance that will one day blend its stars with ours. In the end, meeting Andromeda is not really about charts or coordinates, or even about astronomy as a subject in school. It is about a moment of recognition, a moment where you allow yourself to feel small and vast at the same time. Small because you are one person under an enormous sky. Vast because your mind is able to hold the idea of a trillion stars at once. And from that moment, questions begin to rise quietly on their own. If you can see an entire galaxy with your eyes, what, exactly, are you seeing? How many stars are hidden in that blur? How far do they spread? And what else might be waiting in the dark, just beyond the edge of what we usually notice? There is a quiet shock hidden in that first moment when you really understand what you are looking at. You stand under the sky, find that faint blur of Andromeda, and someone tells you that's an entire galaxy. And your mind does a small double take. Because if you can see a whole galaxy with your eyes, the next thought almost has to be, how big are galaxies really? We use the word galaxy so casually. It sounds like just another space word, sitting next to planet and star and comet, as if it were just the bigger cousin in the same family. But a galaxy is not just a large star. It is a different kind of thing, a structure so large that our normal sense of size starts to wobble when we think about it. Calling a galaxy big is a bit like calling the ocean damp. Technically right, but far too small for what you are describing. It helps to start at home. Think about our own galaxy, the Milky Way. Astronomers think it holds around 400 billion stars. Try not to rush past that. Each of those stars is a sun. Not a tiny dot on a page, but a huge ball of hot gas, shining for billions of years. Many of those suns have planets. Some rocky, like Earth, some giant and gaseous, some with moons. Around each star is its own little system of orbits and temperatures and possibilities. The space between all those stars is not empty. It is full of thin gas, tiny grains of dust, light and radiation passing through, magnetic fields threading across space, and a vast halo of invisible matter that does not shine at all, but pulls on everything with gravity. All of that together, the stars and the gas and the dust and the hidden mass, is what we mean when we say the Milky Way. Even that is already beyond normal experience. And yet, by the standards of the universe, our galaxy is not special. It is not especially huge. It sits somewhere around average, modest next to the real giants. And one of those giants is our neighbor, Andromeda. Andromeda. When scientists talk about Andromeda's size, one of the simplest things they mention is its diameter. The main disk of the galaxy, the flat, spiraling part where most of the stars live, is about 220,000 light-years wide. That number is easy to say. The meaning takes longer. A light year is how far light travels in 1 year. Light is the fastest thing we know. It races through space at about 300,000 kilometers every second. In 1 year of constant travel, it covers nearly 10 trillion kilometers. That is 1 light year. Andromeda's disk is about 220,000 of those distances, laid side by side. If you could somehow move at the speed of light, which we cannot, you would still need 220,000 years to travel from one edge of Andromeda's disk to the other. If you tried to turn that into kilometers by multiplying it out, the number would be so huge that it would stop feeling like a number at all. It would just become a string of digits your mind cannot hold all at once. And that is only the bright part. Around the disk, stretching much farther out, is a halo of dark matter. It does not glow, but it has mass. Its gravity shapes the orbits of stars, holds the galaxy together, and may extend for 1 million light-years or more. When you include that, Andromeda becomes less like a flat coin of stars and more like a deep, invisible bubble of influence in space. To get a sense of the difference in scale, it helps to bring it closer to home. Our whole solar system, from the Sun all the way out to the distant cloud of icy comets at the edge, is around 2 light-years across. That is already huge. The spacecraft we have sent out are only just now approaching that distant region after decades of travel. Andromeda could fit that entire 2 light-year span, not once, not a few times, but well over 100,000 times across its width. Putting the solar system and Andromeda in the same unit of measurement, light-years, almost feels unfair. It is like using the same word step for both one pace across a room and a hike across a continent. Technically you can, but the stretch is enormous. Another way to approach it is by counting stars. As far as we can tell, Andromeda holds close to 1 trillion stars. 1 trillion is 1,000 billion. Imagine you try to count them, one star every second, no breaks. You would be counting for more than 30,000 years. And by the time you finished, your count would already be wrong, because new stars would have been born and others would have died while you were counting. Each of those stars is a sun in its own right. Many of them will have planets. Some of those planets will have moons. The number of possible worlds inside one galaxy is so large that it stops being something you can picture. You can only point at it and say, "That is a lot," and let the feeling sit there. And then, once you have done all that work to get your head around one galaxy, you remember that Andromeda is just one among hundreds of billions of galaxies in the observable universe. Suddenly, what felt unique becomes ordinary. Galaxies like Andromeda are scattered through space like lanterns in a dark field, each one enormous. Each one with billions or trillions of stars. Our minds want to treat them as rare, but the universe treats them as common. The structure of it all builds upward, in layers. Inside Andromeda, there are individual stars and planets. Those are arranged into solar systems. The systems cluster along spiral arms. The arms together make up the galaxy. That galaxy sits in a small group with others. Our Milky Way and Andromeda share this local group, about 50 galaxies bound together by their mutual gravity. The local group sits inside a larger supercluster of galaxies, and that supercluster is just one thread in an even larger web of matter that stretches across the universe. At each step, the scale jumps. Solar system, galaxy, group, supercluster, cosmic web. The canvas keeps getting bigger, and the thing you were just struggling to imagine is suddenly tiny compared to the next level up. Because the numbers get so extreme, astronomers lean on analogies to help. They might say, if the solar system were the size of a coin, Andromeda would be the size of a continent. Or if you shrank the Milky Way down until it was a dinner plate, Andromeda would be another plate beside it. And all the galaxies we can see would cover a whole Earth-sized ball with plates. These pictures do not capture everything, but they give the mind something to hold, some way to shrink the unimaginable down to a kitchen table or a globe. Or they might say this: imagine the Earth as a single grain of sand, then picture every grain of sand on every beach, on every coastline on the planet. Even that would not equal the number of stars in Andromeda, and Andromeda is only one galaxy among many. The point is not to get an exact count. The point is to feel how far the numbers reach beyond what we usually play with. The first time this really lands for someone, it can gently rearrange how they see themselves. Most of our worries and plans live on human scales, meters and kilometers, minutes and kilometers, minutes and kilometers, minutes and kilometers. When we stretch our thinking, we might reach centuries, maybe a few thousand years of history. Galaxies move on scales of millions and billions of years and distances of hundreds of thousands of light years. Our entire recorded history becomes a thin pencil line on a wall that stretches beyond sight. And yet, here we are on that tiny line, noticing all of this, asking questions about it, measuring, comparing, building ideas big enough to hold, at least in symbols, these enormous structures. It is worth remembering that it took us a long time to even understand what a galaxy is. For centuries, Andromeda was just a fuzzy patch, a nebula assumed to live within the Milky Way. The idea that it might be a whole separate system of stars was debated. It was only in the 1920s, when Edwin Hubble measured the distance to Andromeda using special pulsating stars, that it became clear this blur was far, far beyond our own galaxy. That single realization blew open the size of the universe in our minds. Overnight, the Milky Way went from everything to one of many. The immensity of galaxies is not only about distance, it is also about time. Stars in Andromeda have been shining for billions of years. Whole generations of stars have lived and died there. In their cores, they fused hydrogen into heavier elements. In their deaths, especially in supernova explosions. They scattered those elements back into space. New stars formed from that enriched material. New planets formed from the leftover dust. This has been happening over and over, long before Earth existed, and it will continue long after our own sun is gone. When you look at Andromeda, you are seeing one frozen moment in that long story. One frame in a film that has been playing for billions of years and will keep playing for billions more. You are seeing stars that are older than the Earth, and stars that are young, on cosmic terms. You are seeing the result of countless cycles of birth and death, and recycling of matter. And here is the part that loops it back to you. The atoms in your body were made in processes like that. The carbon in your cells, the calcium in your bones, the iron in your blood. All of these came from stars that lived and died in some galaxy, somewhere before our solar system formed. We call it stardust, and that is not just poetic language. It is a literal description of where the material came from. So the immensity of galaxies is not something completely outside of us. It is the larger version of the same story that built us. When you look at Andromeda, you are seeing a place made of the same kind of matter as you, the same chemistry, the same physics, just stretched across a vastly larger space and time. The faint patch in the sky is a doorway into that realization. It is the first small glimpse of how large the universe really is, and how tiny we are in comparison, and yet how deeply connected we are to it all. That mix of smallness and connection can feel overwhelming, but it can also be strangely gentle, comforting even, because once you see that this one blur is an entire galaxy, and that galaxies like it are everywhere, and that you are made of the same kind of stuff, some of the sharp edges of importance start to soften. Your problems are still real. Your life is still real. But they sit now against a backdrop that is much, much larger. The questions that rise out of that. What does this mean for our place here? How do we live knowing this? Don't need fast answers. They are the kind of questions you can simply rest with, letting them drift at the edge of your thoughts like a quiet tide as you fall asleep, with a galaxy in your mind and starlight in your veins. When we talk about Andromeda, it is easy to picture it drifting alone in a huge black emptiness, one bright island of stars in a silent, endless sea. That image feels clean and simple. One thing against nothing. But the universe is not arranged that way. Galaxies are social creatures. They gather. They cluster. They fall into groups where gravity quietly keeps everything in the same slow conversation. Andromeda, even with all its size, is not wandering on its own. It lives in a small community of galaxies. Our community of galaxies. Our community, the one we happen to share. Astronomers call this little gathering the local group. It sounds grand, but in cosmic terms, it is a modest arrangement, not a crowded metropolis. More like a small town on the edge of a very large map. There are more than 50 galaxies in this group, but almost all of them are tiny. Most are dwarf galaxies, each one holding only a few million or tens of millions of stars. That sounds big to us, but beside Andromeda, they are like porch lights next to a city. At the heart of this group are two main giants, our own Milky Way and the Andromeda Galaxy. Both are large spirals. Both are wrapped in huge halos of invisible mass. Together, they set the rhythm of the whole neighborhood. Their gravity reaches the farthest, their motions shape where everyone else can go. There is also a third important member, a smaller spiral called the Triangulum Galaxy. It is not as big as the other two, but it is still far from small. It may even orbit Andromeda like a distant companion. These three together form the spine of the local group, and among them, Andromeda seems to be the heavyweight. The largest house on the cosmic street. To picture this, it can help to imagine a quiet town spread across a wide valley. Most of the buildings are tiny cabins and cottages, spaced out along the hills, but here and there, a few huge old mansions rise up, full of rooms and staircases and lights. Those mansions are Andromeda and the Milky Way. They are the ones you notice as soon as you look. Everything else All the little houses exists in their shadow. The dwarf galaxies are those small homes. Some circle close to the Milky Way, like the large and small Magellanic Clouds in our own sky in the southern hemisphere. Others circle near Andromeda, like M32 and M110. Those two are small, rounded galaxies that sit close beside Andromeda's disk, like friends walking next to a much taller figure. Each dwarf has its own stars, its own history, but their paths are pulled and stretched by the larger galaxy's gravity, the way a small boat rocks in the wake of a passing ship. If you could somehow hover above the local group and look down, you would see Andromeda on one side and the Milky Way on the other, separated by about 2.5 million light-years of space. Between them lies mostly thin gas and scattered dwarf galaxies. Off near Andromeda, you would see Triangulum, keeping it company. The other small galaxies would be spread around in all directions, some clinging closer to one giant, some to the other, all of them held in place by the combined pull of their mass. From edge to edge, this whole group would span around 10 million light-years or so. That is enormous by any human measure. But if you zoomed out further and looked at larger clusters of galaxies and superclusters beyond them, the local group would start to look small. A quiet suburb at the edge of a much larger cosmic city, not a busy downtown. Just a calm corner where a few big spirals and many smaller dwarfs share the same long fate. Andromeda's role in this little suburb is not just to be one more house on the lane. It seems to be the heaviest resident. Its total mass, including all that unseen matter around it, is probably greater than the Milky Way's. Maybe by a third, maybe by half. We are still refining the numbers, but whatever the exact amount, that extra weight gives it a stronger grip on the galaxies around it. When astronomers run computer models of the local group, they see Andromeda and the Milky Way moving toward one another, slowly, pulled by their mutual gravity. That pull is stronger than the general expansion of the universe at this scale. The two giants are locked in a slow ballet that will bring them together in about 4 billion years. When that happens, their stars, gas, and dark matter halos will mix. The local group will not be built around two spirals anymore, but around one giant merged galaxy. That distant future meeting is not just a dramatic event. It also tells us that Andromeda is one of the main shapers of what this group will eventually look like. Its gravity, along with the Milky Way's, decides how the smaller galaxies move, which ones survive as separate objects, and which ones get slowly torn apart and absorbed. If we turn our attention from the big players to the small ones, the picture shifts again. Some of the dwarf galaxies around us are so faint and spread out that we only discovered them recently, using deep, sensitive surveys. They are not neat spirals. Some look like fuzzy, irregular patches of stars without a clear shape. Others are more like pale, smooth ellipses, featureless to the eye. Many of them are being slowly tugged by the bigger galaxies, their stars stretched into thin streams that wind through space. These small companions are reminders that galaxies come in, all sizes. Not every galaxy is a grand spiral like Andromeda. Some are messy clumps, some are fragile, barely held together. Some are leftovers from older collisions. In this sense, the local group is not just defined by its two giants. It is defined by the relationship between large and small, by how the big galaxies treat their tiny neighbors, and how the tiny galaxies in turn leave traces in the halos of the giants. Without Andromeda, the local group would be very different. The Milky Way would dominate more completely. The balance would shift. With Andromeda present, there is a kind of symmetry. Two large spirals facing each other, across a gulf of space, drawing in the smaller galaxies between them. It is like a dance between two heavy partners, with everyone else moving in response to their steps. For astronomers, this little community is more than just home territory. It is also a kind of laboratory. Because it is nearby, we can study its members in far more detail than distant galaxies. We can resolve individual stars in Andromeda. We can watch how dwarf galaxies are being pulled apart. We can measure motions, shapes, star formation, and interactions across the group. By comparing Andromeda, the Milky Way, Triangulum, and all the dwarfs, scientists can test ideas about how galaxies grow, how they merge, and how their environments change them over time. In that way, Andromeda's place in the local group is not just about where it sits in space. It is about what it teaches us. It is a key piece in the puzzle of how galaxies live together. It shows us that big galaxies build themselves partly by swallowing smaller ones. It shows us that even a small group of galaxies is full of movement and history. There is also something quietly comforting about realizing that galaxies fall into groups like this everywhere. The local group is not special. All across the universe, galaxies cluster together, linked by filaments of matter, like threads in a web. No galaxy is truly alone. Everything is connected by gravity, woven into the same large-scale structure. We simply happen to live in this particular group, with this particular neighbor. That alone gives Andromeda a kind of familiarity. It is our closest, large spiral companion. We share a future with it. We share smaller neighbors with it. When you picture the local group, you are really picturing our cosmic neighborhood, the part of the universe we can honestly call home. So when you think back to that faint blur of light you can see with your own eyes, you can add another layer to it now. That blur is not only an immense galaxy on its own, it is the biggest galaxy in a family of more than 50. It is an anchor, helping to hold that family together. It is a neighbor, facing our own galaxy across empty space. It is a counterpart, equal to us in importance on this small cosmic street. The corner of the universe we inhabit is shaped by this relationship, the Milky Way on one side, Andromeda on the other, everything else moving in between. When we picture our place in the universe, we almost always start from the Milky Way. It feels natural to treat it as the default, the template, the way a galaxy is supposed to look. It is our home. Its stars are the ones that have shaped every night sky any human has ever seen. But as soon as you place the Milky Way beside Andromeda in your mind, the picture softens and changes. Suddenly, our home is not the standard anymore. It is one example. Andromeda is another. Two galaxies that look similar in broad strokes, but in the details turn out to be their own strange, specific things. Both are spiral galaxies. Both have a bright center and arms that curl outward. Both are filled with stars, gas, and dust. Both are wrapped in halos of invisible matter. On paper, they sound like twins. But if you look more closely, you start to notice the differences. The way you can tell two trees of the same species apart when you really study their branches. The Milky Way is what astronomers call a barred spiral. Imagine a bright, central bulge of stars, and then imagine a straight bar of stars running through that bulge, like a beam across the middle. From the ends of that bar, long spiral arms unwind and sweep outward. That bar is not just decoration. It guides gas and stars toward the center. It shapes the flow of material in our galaxy. It helps decide where new stars will form. Andromeda is also a spiral, but the bar, if it has one, is not as clear. Its central bulge is rounder and more pronounced, almost like a bright, glowing egg in the middle. Its arms are broad and heavy with dust, less delicate and more thickly painted across the disk. This gives it a slightly different personality. If the Milky Way is a spiral, drawn with a fine brush, Andromeda is one painted in wider strokes. In terms of simple size, Andromeda seems to be the big sibling. Our best estimates say that Andromeda's main disk is roughly twice as wide as the Milky Way's. If you could somehow set the two next to each other on a dark table, Andromeda's disk would spread farther out, its arms reaching more deeply into space. The difference in population is similar. The Milky Way likely has a few 100 billion stars. Andromeda may have something close to 1 trillion. That is not just a bigger number. It means that if each star were a candle, Andromeda would be a much more crowded city of lights. Each of those stars has the chance to host planets. Each of those planets, the chance, however small, to host something interesting on its surface. When we talk about mass, things get a bit more mysterious. Most of the mass in both galaxies is not in the stars we see. It is in the dark matter we do not see. That makes precise measurements difficult. Some studies suggest Andromeda could be about 1.5 times as massive as the Milky Way. Others say the two are closer to equal than we once thought. The numbers shift as we improve our methods. But even with that uncertainty, Andromeda is usually treated as the heavyweight of the local group. Its gravity reaches a bit farther. Its pull is a little stronger. In the quiet tug-of-war that shapes our small corner of the universe, it is the slightly heavier partner. None of this means the Milky Way is just a smaller copy. It has its own strengths. Its bar in the center changes how gas flows in. It may be forming new stars at a faster rate than Andromeda right now, making it more active in some regions. Our galaxy also hosts its own impressive set of companions, like the large and small Magellanic Clouds, which appear in southern skies as their own pale smudges of light. The cores of the two galaxies are another place where contrasts appear. At the center of the Milky Way sits a supermassive black hole, nicknamed Sagittarius A. It has a mass of a few million suns. That is already hard to imagine. But the black hole is far larger, with a mass tens of times greater.
Getter, Brady.
If our central black hole is a mountain, Andromeda's is a whole mountain range. That huge difference gives Andromeda a stronger gravitational anchor in its inner regions. Stars near its center move under the influence of a heavier, deeper well of gravity. And yet, despite its size, Andromeda's core is relatively quiet compared to the most violent black holes we see in distant galaxies. It is not currently feeding in large amounts of gas. It is more like a great dormant engine, idling softly rather than roaring. Even the spiral arms tell slightly different stories. The Milky Way's arms are thought to be more loosely wound, giving our galaxy a somewhat open, airy pattern. Andromeda's arms look broader, more thickly dusted with dark lanes of material. In photographs, they appear more dramatic, with strong contrast between bright star-forming regions and shadowy gaps where dust blocks the light. Part of this patchwork of similarities and differences likely comes from their pasts. Neither galaxy has had a quiet life. Both have eaten smaller galaxies over time. The Milky Way shows streams of stars in its halo that used to belong to dwarf galaxies now being torn apart. Andromeda, too, is wrapped in faint arcs and currents of stars that seem to be leftovers from older mergers. These past encounters have stirred their disks, bent their arms, and fed their central regions. No two galaxies have exactly the same history, so no two look exactly the same. It is tempting to turn all of this into a contest. Which is bigger? Which has more stars? Which is better? But the universe is not really interested in that kind of ranking. The Milky Way and Andromeda are not rivals. They are partners in a shared story. Their masses pull on each other. Their satellites orbit in patterns shaped by both. Their futures are already linked by gravity in a slow, inevitable approach that will end with them merging into one larger galaxy. For us, thinking about their relationship does more than satisfy curiosity. It changes how we see our own place. If Andromeda is larger, it reminds us that our galaxy is not the final word in galactic design. It is one version among many. If Andromeda's black hole is bigger, it stretches our sense of what galactic centers can hold. If the Milky Way is more active in forming new stars, it reminds us that size alone does not define how alive a galaxy feels. There are many ways to be a galaxy. Visibility is another interesting contrast. We live inside the Milky Way's disk, so we see it as a river of light across the sky, thickest along the plane where we look through the most stars. We never get an outside view. We cannot step back to see the whole spiral at once. We have to reconstruct it using clues. How stars move, how gas is arranged, how radio waves map the disk. Andromeda, on the other hand, is far enough away that we do see it from the outside. Tilted toward us, its disk and bulge and arms show up as a single coherent object in the sky. By studying Andromeda, we are partly studying a stand-in for our own galaxy. It gives us a model of what a big spiral looks like from outside. In a way, Andromeda is like a mirror. We can't see ourselves in directly, but we can see something very similar and learn about our own reflection. Both galaxies share the same environment too. They sit in the same local group, surrounded by a cloud of small companions, but their families are not identical. Andromeda's satellites include bright companions like M32 and M110, along with a swarm of faint dwarf galaxies only recently discovered. The Milky Way satellites include the Magellanic Clouds and many tiny dwarfs that barely show themselves as slight overdensities of stars. By comparing these satellite systems, astronomers can ask questions like, how many small galaxies should a large one have? How many get torn apart? How does the local environment change a dwarf galaxy's fate? The differences between Andromeda's collection and the Milky Way's help refine our answers. One of the most interesting lessons in all of this comparison is how much we still do not know. We are not entirely sure which galaxy is more massive. We do not know every detail of their past merger histories. We are still discovering new satellites. Our measurements keep improving. Numbers we thought were firm get adjusted. Pictures we thought were complete gain new pieces. This uncertainty is not a failure. It is a sign that galaxies are alive in time, and that our understanding of them is alive too. They are not simple objects you can measure once and be done with. They are changing systems, and our knowledge is a changing system trying to keep up. So when you place the Milky Way and Andromeda side by side in your thoughts, you are not just seeing two big spirals floating in space. You are seeing two variations on a theme, two different ways the same basic ingredients, stars, gas, dust, dark matter, can arrange themselves over billions of years. Each has its own history, its own internal rhythms, its own way of shining. Together, they outline the shape of our cosmic neighborhood. One is the home we live in. The other is the neighbor we watch in the sky. And between them, in the quiet pull of their gravity and the slow approach of their future meeting, we see not a competition, but a relationship. A reminder that even on the scale of galaxies, nothing truly exists alone. If you stand under a dark sky and find that tiny blur of Andromeda, it's almost absurd to think that we've put numbers on it. There it is, looking like nothing more than a thumbprint of light. No detail, no depth, just a smudge. And yet, somewhere in that smudge are distances in the millions of light years, star counts in the trillions, and masses we can only describe by comparing them to suns. It feels, at first, like the kind of thing humans shouldn't be able to measure at all. How do you weigh something you can't touch? How do you mark the size of something you can't walk across, can't circle with a spacecraft, can't even see clearly with your own eyes? The answer, every time, comes back to light. Light is the only messenger that makes it across that gulf to us. Every photon that reaches your eye, or a telescope's mirror, has traveled for millions of years, carrying with it tiny hints about where it came from and what it passed through. Hidden in that glow are clues to distance, speed, composition, and mass. Astronomers have spent generations learning how to read those clues. One of the simplest ideas hides in something you already know from everyday life. A nearby lamp looks bright. The same lamp far away looks faint. How bright something appears to you depends on two things at once: how much light it's really giving off, and how far away it is. The farther away it is, the more that light spreads out, and the dimmer it seems. Turn that idea around, and it becomes a measuring tool. If you can find an object in the universe whose true brightness you know, then the amount of dimming you see from Earth tells you how far away it must be. These cosmic reference lights are called standard candles. They're like streetlights of known wattage scattered through the universe. One of the most important kinds of standard candle is a class of stars called Cepheid variables. These stars do something very convenient for us. They slowly pulse in brightness over time. Bright dim, like a gentle, regular heartbeat, And the length of that pulse is directly tied to how luminous the star actually is. A Cepheid that takes longer to cycle from bright to dim and back again is intrinsically brighter than one that pulses quickly. By measuring how long it takes a Cepheid's light to rise and fall, astronomers can figure out its true brightness. Then they compare that true brightness to how faint it appears from Earth. The difference between those two tells them the distance. It's like knowing how powerful a lighthouse is supposed to be, and then, from how faint you see it, working out how far you must be from shore. This trick was the key that unlocked Andromeda. In the 1920s, Edwin Hubble turned a large telescope toward that fuzzy patch and carefully photographed it over time. In those images, he spotted Cepheid variables sprinkled inside the blur. He measured their pulsations, calculated their true brightness, and from that worked out how distant they must be. The answer was shocking for the time. Those stars were far beyond the boundaries of our Milky Way. Andromeda was not a little nearby cloud in our own galaxy. It was a galaxy itself, a vast system, separate from ours. With a single set of measurements, the size of the known universe exploded in our minds. The smudge became a world of its own. Since then, astronomers have added more tools to their measuring kit. Some are even more powerful than Cepheids. Certain kinds of exploding stars called supernovae can also act as standard candles. A particular family of them tends to blow up with very similar brightness each time. When one of these eruptions goes off in a distant galaxy, astronomers measure its light curve, how it brightens and fades, and use that to estimate how luminous it truly was. Then, just like with Cepheids, they compare true brightness to apparent faintness to get a distance. Supernovae are so bright that we can see them across much greater stretches of space than individual Cepheids. In Andromeda, we have seen such explosions and used them to refine our sense of how far away the galaxy really is, checking and sharpening the numbers that began with Hubble's work. Another kind of information is carried not in how bright the light is, but in its color, more precisely, in its wavelength. When an object in space is moving away from us, the light it sends is stretched slightly, shifted toward the red end of the spectrum. When it's moving toward us, the opposite happens. The light is compressed a little, shifted toward the blue. This is called redshift and blue shift. Most distant galaxies show redshift because the universe is expanding and they are receding from us. Andromeda is one of the odd ones. Its light is slightly blue shifted. That tells us it is heading in our direction. By measuring exactly how much its light is shifted, astronomers can calculate its speed relative to us, about 100 kilometers per second on average, closing the gap. That number feeds into the story of our eventual collision with Andromeda in a few billion years. Distance and speed are one part of the puzzle. Size is another. To measure size, astronomers use a simple geometric idea. Anything you look at in the sky covers some angle. The moon takes up about half a degree. Your little fingernail held at arm's length is about a degree. If you know how far away an object is, and you know how wide it appears in angle, you can work out its true width. Andromeda stretches over several degrees of sky, if you include its faint outer arms. But most of that is too dim for the naked eye. Using telescopes and cameras, astronomers can map that full angular size. Combine that with the distance from standard candles, and you get a physical diameter, around 220,000 light-years, for the bright disk. It sounds almost too straightforward, angle plus distance equals size, but every step depends on the earlier work of measuring distance correctly. Mass is trickier still, because you can't see mass directly. You infer it from motion. Stars in a galaxy orbit the center, just as planets orbit stars. The speed at which they orbit depends on how much mass is pulling inward with gravity. If you can measure how fast stars and gas are moving at different distances from the center, you can work backwards to figure out how much mass must be there to keep them in their paths. When astronomers do this for Andromeda, they find something surprising. The outer stars and gas clouds are orbiting faster than they should if the only mass present were from the stuff we can see: stars, gas, dust, According to normal gravity, they ought to slow down farther out, the way planets in our solar system move more slowly the farther they are from the sun. But they don't. Their speeds stay high. The simplest explanation is that there is more mass there than we can see. A halo of dark matter, spread through and around the galaxy, outnumbering the visible mass many times over. We do not know exactly what dark matter is made of, yet, but we can feel its presence in the way it bends the paths of stars. In this way, Andromeda's unseen mass is measured not by sight, but by the dance it forces its stars and gas to perform. As technology has improved, so has the precision of all these measurements. Larger telescopes on the ground, with sharper optics and sensitive detectors, can pick out fainter stars and track their motions more carefully. Space telescopes, like Hubble, avoid the blurring of Earth's atmosphere and can resolve individual stars in Andromeda that would otherwise blur together. We can monitor their brightness over years. We can measure slight changes in light and tiny shifts in wavelength. Every generation of instruments adds a small layer of clarity. Distances are recalculated. Mass estimates are updated. The size of the dark matter halo gets refined. The picture of Andromeda's structure becomes less fuzzy, more detailed, but there is always some uncertainty left, like mist at the edges of what we know. Measuring a galaxy is not like weighing a rock. It is more like trying to figure out the shape and size of an enormous, slowly moving cloud by watching how birds fly through it and how the sunlight changes as it passes. There are always assumptions built into the models, always room for better data, always new questions to ask. Beyond the direct measurements, astronomers also lean on comparisons. They don't study Andromeda in isolation. They look at other spiral galaxies farther away. They ask, if Andromeda's light looks like this and its stars move like that, how does that fit into the patterns we see in spirals elsewhere? They watch how Andromeda's dwarf companions orbit it, and from those motions they infer how far its gravity reaches, how massive its halo must be. Each piece of evidence is one more tile in a mosaic. The result of all this is quietly astonishing. To the naked eye, Andromeda is a faint blur, yet we can say, with some confidence, how far away it is. We have a reasonable estimate of how wide its disk is. We have a sense of its total mass, including both visible and invisible matter. We can even project its motion into the future and see that it is on a path to meet our galaxy. All of that from light, from tiny packets of energy that have been flying through space for millions of years and happen, in the final instant of their journey, to land on the glass of a telescope or the back of your eye. There is something deeply human in this process. No one suddenly knew how to weigh a galaxy. The ability was built slowly, over centuries, first by people who simply noticed the blur, then by those who carefully drew it and wrote about it, then by those who argued about what it might be, then by those who found Cephids and measured their pulses, then by those who split light into spectra and saw shifts in color, then by those who wrote equations to describe orbits and gravity. Each generation added one more rung to the ladder. None of them climbed all the way from the ground to the galaxy alone, but together, they made it possible for us to take something that once felt purely mysterious and give it numbers, distances, masses, paths. And yet, the numbers do not cancel the mystery. Saying 2.5 million light-years is not the same as feeling what that distance means. Saying 1 trillion stars does not mean your mind can truly picture 1 trillion suns. The measurements sharpen our view, but the emotional response remains the same, maybe even stronger, because now, when you look up at that faint blur, you can know both things at once. You can know that it is measurable, its distance, its speed, its size, its mass, and you can know that, even so, it is still vast beyond anything you will ever walk across or touch. It simply lets you see just how large it really is. So the next time you find Andromeda in the sky, you can let two kinds of awareness rest side by side. On one side, the quiet satisfaction that we have, in some sense, turned that blur into a set of numbers. On the other, the soft, humbling realization that those numbers describe a structure far beyond the scale of our lives. Somewhere between those two is the real answer to our question. How big is Andromeda, really? Big enough that we can measure it. Big enough that, even after measuring, it still feels like standing at the edge of an ocean you cannot see across. When most of us picture a galaxy, the first image that floats up is a spiral, a bright center, long arms curling outward. Stars and dust arranged in smooth arcs like brushstrokes on a dark canvas. It almost feels too pretty to be real, like something invented for the cover of a book. But that shape isn't just for show. In galaxies like Andromeda, the spiral is not decoration. It is the structure that tells us how the galaxy breathes, how it moves, where stars are born, and how it manages to stay together over unimaginable stretches of time. If you look at a detailed photograph of Andromeda, the first thing your eye is pulled to is the glowing central bulge. That is the crowded heart of the galaxy. A tight swarm of older stars packed so closely together that their light blends into a smooth, yellowish glow. Around that glow, the galaxy doesn't just stop. Two great arms unwind from it. Like ribbons thrown into slow motion, these arms are not thin lines drawn in the sky. They are wide regions, rich with stars and gas and dust. In color images, they look mottled and textured. You see specks of sharp blue, where young, hot stars are burning fiercely. You see dark streaks where dust clouds block the light, tracing shadows that cut across the glow. The arms look rough, almost grainy, and that roughness is the mark of activity. It is the chaos of things happening, not a smooth, finished surface. It helps to remember that the arms are not solid objects. They are not permanent rails of stars, frozen in place forever. They are more like patterns in motion, regions where matter bunches up, moves through, and spreads out again. A helpful way to imagine it is as a traffic jam on a busy highway. The traffic jam seems like a thing. You can point to it, say, "There it is." But the cars inside it are always changing. New ones enter from behind, others leave at the front. The pattern stays, the cars do not. The spiral arms of Andromeda work in a similar way. Stars and clouds of gas move around the galaxy, and as they pass through the arm, they slow and crowd together. The arm is the traffic jam, the stars are the cars. The pattern survives far longer than any single star that currently sits inside it. Inside these crowded arms, new stars are born. Giant clouds of gas drift the galaxy, and when conditions are right, gravity begins to pull them inward, clumping them together. The cloud collapses, breaks into knots, and in those knots, nuclear fusion lights up. A star is born, often not just one, but whole clusters of them, forming together like a litter. The youngest and most massive of these stars burn hot and bright, shining with a bluish light. They live fast and die young, lasting only a few million years before they burn out or explode. Because they are so bright, they act like neon signs, marking the places where star birth is happening right now. That is why the arms of Andromeda sparkle with blue patches in photographs. Each one is a nursery, full of baby stars just starting their lives. Around many of these regions, you will see soft pink glows. Those are clouds of gas, lit up by the harsh ultraviolet light from the youngest stars. The gas becomes excited and glows, outlining the place where it is being carved and shaped by newborn suns. These glowing patches are more clues. They tell us where the galaxy is actively renewing itself. Threaded through all of this are the dark dust lanes. They look like gaps, like someone has taken a brush dipped in shadow and dragged it across the galaxy. But they are not empty. They are full of tiny solid particles and cold gas, the raw material from which future stars and planets will form. In a way, the dust lanes are the seed banks of the galaxy. Without them, the arms would still shine, but they would be fossils. With them, the arms are alive, always in the process of becoming something new. When you trace the shape of Andromeda's arms, you are tracing its ongoing life story. You are following the paths where stars have been born, lived, and died for billions of years. The spiral is not just a pretty pattern. It is the record of cycles of birth and death, written out across hundreds of thousands of light years. If you look carefully, you will notice that Andromeda's spiral is beautiful but not perfectly neat. One arm might look broader than the other. Some parts are thicker, some thinner. There are knots where clusters are bunched together, and uneven curves where the arm seems tugged or twisted. These small imperfections are clues too. Andromeda does not live alone. It has small companion galaxies that wander near it. When these companions pass close by, or even right through the disk, their gravity pulls on Andromeda's stars and gas. That pull can stretch an arm, bend it, or set off new waves of crowding that ripple around the disk. Over time, each encounter leaves a fingerprint. The spiral you see today carries marks of many such meetings, written into its asymmetries. Our eyes, though, hardly see any of this. To us, under a dark sky, Andromeda is a small, oval blur. The arms are hidden in that blur, their full reach swallowed by faintness. But if your eyes were sensitive enough to catch every bit of its light, the galaxy would spread far across your view. Its disk would cover a patch of sky, many times wider than the full moon. You would look up and see a true spiral hanging over you, arms arching from horizon to horizon, as if an entire whirlpool of stars had been pasted across the dome of night. That is what Andromeda really looks like. The telescopes simply collect enough light to reveal what's already there. The shape is always present. Our vision is just not built to see all of it at once. And the familiar spiral is only part of the story. Beyond the bright arms, Andromeda continues. It is surrounded by a vast, faint halo of stars that stretches much farther than the obvious disk. Scattered through this halo are long, thin streams of stars. These are the remains of smaller galaxies that Andromeda has pulled apart and eaten over time. As a dwarf galaxy falls in, Andromeda's gravity tears it into pieces, stretching its stars into trails that wrap around the main galaxy like ghostly ribbons. Those streams trace Andromeda's history of encounters and mergers. They show us that the galaxy's shape is not fixed. It has been sculpted by what it has swallowed, changed by every past encounter. The spiral arms are simply the brightest part of a much larger, layered structure that reaches far into the darkness. When scientists study Andromeda's arms, they see more than a beautiful swirl. They measure how fast stars are moving in those arms. They map out where gas is dense and where it is thin. They count how many new stars are being born in different regions. They build models to see how a pattern like that can survive for billions of years without getting wound up and erased as the galaxy turns. By comparing Andromeda's spiral with the spirals of other galaxies, they test ideas about how galaxies maintain their shape and balance. The arms become a kind of written record of physics in action. Gravity, motion, pressure, and time all leave their marks there, but on a scale so large that we need mathematics and patient observation to decode it. For the rest of us, those arms are also a reminder of something familiar. Spirals are not just cosmic. They appear in seashells, in the pattern of a sunflower's seeds, in hurricanes swirling on weather maps, in the way water drains in a whirlpool. The spiral is a shape that nature seems to favor whenever there is rotation, growth, and a flow of matter or energy. In Andromeda, that same shape is repeated on a scale of hundreds of thousands of light years. The curve you see in a shell on a beach and a curve you see in a galaxy are distant cousins, shaped by different rules but echoing the same theme. Noticing that is like seeing the universe rhyme with itself. The small and the immense are not identical, but they share patterns. If you imagine drifting closer to Andromeda, leaving our galaxy behind and gliding through the dark between, the arms would slowly swell in your view. From far away, they are graceful lines. As you approach, they turn into regions, then into crowded fields, then into rich star fields full of detail. You would see clusters of stars gathered into bright knots. Some clusters would be huge, with so many stars packed together that they outshine any cluster we have in the Milky Way. You would pass glowing pink clouds where new stars are forming, their light still trapped inside shrouds of gas. You would see dark filaments of dust cutting across these regions like smoke. You would find leftovers of exploded stars, shells of gas expanding outward, marking where a star ended its life in a sudden burst. Up close, the spiral arms would lose their smoothness. They would look more like weather systems, messy, turbulent, full of pockets of calm and storms of activity. Each arm would be a landscape, not a line. One of the quiet gifts of Andromeda is that it helps us understand our own galaxy better. We live inside the Milky Way, tucked into one of its arms. From this position, we can't easily see the overall spiral shape we belong to. It's like trying to see the shape of a forest when you are standing under the trees. By studying Andromeda from the outside, we get a clearer picture of what a big spiral galaxy looks like in full. We can then take that outside view and apply it inward, using it as a guide to interpret the hints we see from within the Milky Way. How our own arms might be arranged, how our own star-forming regions line up, how our own dust lanes thread through the disk. Andromeda becomes a kind of mirror, reflecting back a possible image of our home that we can't see directly. There is also the dimension of time woven into these arms. A galaxy does not spin like a solid disk. Stars closer to the center orbit faster. Stars farther out move more slowly. If the arms were made of fixed stars, they would twist tightly and smear out over billions of years, but they do not. The pattern of the arms persists because the crowding itself moves through the disk like a wave. Stars move in and out of the arms. Gas flows through, is compressed, forms stars, and moves on. So the spiral you see in Andromeda today is not the exact same spiral that existed a billion years ago. The pattern is similar, but the cast of stars has changed. It will not be the same a billion years from now either. The arms are both long-lasting and constantly renewed, enduring in shape, changing in detail. When we say Andromeda is about 220,000 light-years across, we are really measuring how far that spiral pattern reaches. It is the distance from the tip of one arm on one side of the disk to the tip of another on the other side. Without the arms, the galaxy's bright core would be much smaller. The arms are what stretch it across space and make it truly immense. In that sense, the spiral is not just a look. It is a measure, a record of how far this galaxy extends, of how wide its influence spreads, of how much room its cycles of star birth and death have to play out. When you follow those arcs in your imagination, you are tracing paths far longer than your mind is naturally comfortable with. That uneasy stretch, that feeling that your thoughts are reaching for something just beyond what they can fully grasp, is part of the answer to our question. How big is Andromeda, really? It is as big as the reach of its spiral. As broad as those waves of stars and gas and dust that curl outward into the dark. As vast as the pattern that keeps repeating quietly. On a scale our imagination is still learning to travel. If you could somehow stand beneath Andromeda itself, as if the whole galaxy were hanging just above your head, one of the most startling things wouldn't be its size across the sky. It would be the simple fact of how many suns are packed into that shape. You look up from Earth and you see a blur, soft, quiet, almost shy. And then someone tells you that inside that blur, there are not just a few stars, not just millions, but something like 1 trillion of them. 1,000 billion suns, each one as real as our own. The mind almost refuses to cooperate at that point. We're good at tens, we're decent at hundreds. We can kind of stretch to thousands if we imagine a stadium or a city, but once we step into the realm of billions and trillions, the numbers stop feeling like quantities and start feeling like fog. They're too large to attach to anything in daily life, so astronomers do something clever. They don't pretend they can literally count each star. Andromeda is far away. Its stars are crowded together. Even the best telescopes see many of them as merged light. Instead, They work with the glow as a whole. Every star, no matter how faint, adds a little bit to that glow. Altogether, the galaxy shines with a certain total brightness. By measuring that overall light very carefully and comparing it to models that say, if you have this mix of star types, you get this much light, astronomers can work backward. They can ask, how many stars would we need, on average, to produce what we're seeing? It's not a star-by-star headcount. It's a census built from averages and probabilities. It assumes a certain mix of small stars, medium stars, and rare giants. There is guesswork, but it's informed guesswork, grounded in what we see in nearer parts of the universe where individual stars can be studied in detail. The answer that falls out of that kind of math is staggering. To get Andromeda to shine the way it does, you need roughly 1 trillion stars. If you tried to count them one by one, whispering 1, 2, 3 and so on, saying one number every second, without stopping, day and night, you'd still be counting more than 30,000 years later. By then, whole generations of stars in Andromeda would have lived and died. Your list would be out of date before you were even a tiny fraction of the way through it. That alone tells you something important. The count is symbolic. It's not about precision down to the last star. It's about getting a sense of scale, enough to appreciate that. When we say galaxy, we are talking about a city of suns, far beyond any number our minds are built to handle comfortably. And those suns are not identical lamps. They're a mixed crowd. The majority are tiny red dwarfs, small, cool, and dim. And two, most crowd and dim. They don't shine brightly, but they last an incredibly long time, sometimes longer than the current age of the universe. If Andromeda were a city, these red dwarfs would be the countless small houses that barely glow from a distance, but together make up most of the neighborhoods. A smaller portion of the population are stars something like our sun, steady yellowish, burning calmly for billions of years. They're bright enough to be seen across great distances, but they are still modest compared to the real show-offs, and those show-offs are the massive, hot, blue stars. They burn furiously and live fast, pouring out light and energy, carving their surroundings, and then dying young in cosmic terms. After only a few million years. They are the ones that trace out the spiral arms, the ones that make Andromeda's arms sparkle in photographs. They're rare, but they leave a dramatic mark. Astronomers don't just look at the brightness of Andromeda as one lump. They spread its light out into a spectrum, like a rainbow stretched thin. In that rainbow they can see fine lines and patterns, fingerprints of the atoms inside the stars. By studying those fingerprints, they can tell what kinds of stars dominate the light, how hot they are, what elements they contain. From that, they can build up a picture of the galaxy's stellar population. What fraction are old, cool stars? What fraction are young and hot? How many intermediate stars like the Sun are likely to be there? And once they know that mixture, they can estimate not just how many stars exist, but also how much mass they represent in total. Hidden in that mix is a kind of time capsule. Andromeda has not always formed stars at the same rate. There have been eras when it was very busy, building lots of new stars from its clouds of gas, and quieter times when star formation slowed. The traces of those eras are written into the populations we see now. The young blue stars and glowing gas clouds mark the recent chapters. The older redder stars filling the bulge and halo point back to earlier periods, billions of years in the past. The overall blend is like the rings of a tree, telling the story of how the galaxy has renewed itself over time. One of the most humbling parts of thinking about these trillion stars is remembering that many of them have their own planetary systems. We now know that planets are common, not rare. Small stars have planets, sun-like stars have planets, and even some giants may host them. To say Andromeda contains 1 trillion stars is, indirectly, to say it may contain trillions of worlds, planets, moons, icy bodies, rocky surfaces, gas giants. Most of those worlds will be bare rock or gas, frozen wastelands or scorched deserts. But even if only a tiny fraction are gentle enough for complex chemistry, that tiny fraction, multiplied by such an enormous base number, is still huge. The potential for variety is beyond anything we could ever visit or catalogue. The numbers refuse to shrink into something comfortable. To visualize it, you can start closer to home. On a very dark night, far from city lights, you might see a few thousand stars with your naked eye. It already feels like a lot. Through a small backyard telescope, that number explodes. Suddenly, there are tens of thousands, then more, crowding together in the Milky Way's band until you can no longer tell where one ends and the next begins. Now take that feeling of too many to count and scale it up by hundreds of billions. That's Andromeda. Every tiny point of light you'd see in its disk, every faint shimmer in its halo, is another sun. Our richest night sky is just a miniature version, a small, still life compared to the immense mural that a whole galaxy represents. And those stars are not just sprinkled like glitter. They're part of Andromeda's structure. They orbit the galactic center, along paths controlled by gravity. Some loop close in tight, rapid circles near the core. Others travel wide, slow arcs far out in the disk. Their combined mass keeps the spiral arms from flying apart, holds the galaxy together, and helps determine how it interacts with other galaxies. In its halo, many of the stars are not original to Andromeda at all. They are leftovers from smaller galaxies it has consumed. As those dwarfs fell in, Andromeda's gravity tore them apart. Their stars were flung into long streams, stretched and wrapped around the main galaxy like strands of silk. Over time, these stars blend into the background population, but careful measurements can still pick out their common motion and chemistry. Every time Andromeda absorbs another small galaxy, its star count ticks upward, its total mass grows, its structure changes slightly. The trillion stars we speak of are not the same trillion that existed a few billion years ago. Some have died, others have been born, new ones have been added from the outside. The number is a snapshot in an ongoing process of growth. Compared to Andromeda, the Milky Way, with its few 100 billion stars, suddenly feels modest, still huge, beyond our daily sense, but no longer the giant we might once have assumed it to be. Andromeda is the heavyweight of our little cosmic neighborhood, not only in width and mass, but in sheer population. That difference will matter when the two galaxies eventually meet. When they merge, their stars will be mixed into one larger system. The resulting galaxy will hold more than 1.5 trillion stars, reshuffled into new orbits, new patterns of light. The city of stars will become a megacy, its skyline rewritten. Counting stars in a galaxy may sound abstract, like something done only for the satisfaction of having a big number to quote. But it has real consequences. The number of stars tells you how much light the galaxy produces, how much mass is bound up in luminous objects, how strong its gravity is, how it will tug on its neighbors, how it will evolve over time. It also shapes the way we think about life beyond Earth. Our own galaxy offers billions of potential homes for planets. Andromeda, with its larger population, offers even more. We may never know what those worlds hold, but the act of counting, of turning a blur into about 1 trillion, opens a door in the imagination. It takes some stars over there and turns it into a vast, crowded universe of possibilities. So the next time you find Andromeda in the sky, and it looks small and almost fragile, you can let the two truths sit together. On one level, it is just a smudge, something you could almost miss if you weren't looking carefully. On another level, that smudge is a city of stars so large that if every star were a person, it could hold all the people who have ever lived on Earth, not just once, but many, many times over. Knowing that doesn't make the blur less gentle. It makes it richer. It stops being just a patch of light and becomes a metropolis of suns, shining softly across millions of light years, arriving all together in that subtle, quiet glow your eyes can just barely catch. When most people picture a galaxy, the mind goes straight to the stars, tiny bright points scattered on a black canvas. millions, billions of them forming spirals and halos, like glitter thrown across the void, that if you could zoom in between those stars, you'd find that the spaces are not really empty. The quiet darkness in between is filled with something softer and more hidden. Thin, drifting material that doesn't shine much on its own, but decides how everything else can shine. Dust and gas. It sounds small. Dust makes you think of specks on a bookshelf. Gas makes you think of something that just blows away. But in a galaxy like Andromeda, dust and gas are not minor details. They are the lungs and bloodstream of the whole system. Without them, Andromeda would be a frozen arrangement of aging suns, glowing more weakly with each passing billion years, until it faded. With them, it can renew itself. It can keep making new stars. It can change. Most of this material lives in the galactic disk, wrapped into Andromeda's spiral arms. Imagine broad, invisible rivers flowing along those arms. Not water, but hydrogen gas, drifting in enormous clouds that can stretch for hundreds of light years. These clouds are cold and dim. Left alone, they would stay that way, but the galaxy does not leave them alone. Gravity pokes at them. Shock waves from old, exploded stars ripple through them. Interactions with other clouds stir them up. Little by little, parts of a cloud begin to collapse inward under their own weight. As the material falls in, it heats up. The center grows denser. At a certain point, the squeeze becomes so intense that nuclear fusion starts. And just like that, a star is born. Dust is mixed into these clouds as tiny solid grains, bits of heavier elements like carbon, oxygen, and silicon, all forged in previous generations of stars. These grains scatter and absorb light. These grains scatter and absorb light. To us, they look like darkness. If you see a photograph of Andromeda with dark streaks cutting across the bright arms, that's dust doing its work, blocking the starlight behind it, turning solid light into a patchy, mottled texture. To the eye, it's easy to think there is nothing there, but that nothing is actually potential. It is material waiting to be turned into new stars and new planets. Inside the densest parts of these clouds, the temperature can drop low enough for atoms to link into molecules. Hydrogen joins hydrogen to make molecular hydrogen. That's when a cloud becomes a proper stellar nursery, a place where gravity can start gathering pieces together and turning them into suns. In visible light, these nurseries often look like dark holes. But if you switch to infrared, light our eyes can't see but our instruments can, those same patches glow. We suddenly see filaments, knots, arcs. The cold dust warms slightly and whispers its presence in a different color of light. It's like discovering that what looked like a shadowed doorway is actually a lit room, but only if you put on the right lenses. Astronomers use more than just infrared to follow the gas. Neutral hydrogen, the most common ingredient in these clouds, gives off a very specific kind of radio wave. Its wavelength is about 21 centimeters. Radio telescopes tuned to that note can map where the gas is and how it's moving. When they do this for Andromeda, they see arms of gas reaching even farther than the arms of stars. They see gas orbiting fast enough that the visible matter alone cannot explain the motion. The gas is tracing out the hidden weight of the galaxy. Its dark matter halo. Dust has its own way of talking to us. By absorbing and scattering starlight, it changes the colors we see. Stars behind thick dust look redder and fainter than they really are. That effect, called extinction, can be measured. By comparing how much the light is reddened, astronomers can estimate how much dust lies in the way and where it sits. Infrared observatories like Spitzer and Herschel have shown that Andromeda's dust isn't just randomly smeared around. It collects in rings and arcs, like ripples on a pond. Those rings are clues. They suggest that at some point in the past, a smaller galaxy plunged through Andromeda's disk, disturbing the gas and dust, sending waves of compression outward. Wherever the waves piled material together, new stars would have formed. The dust patterns are memories, frozen shapes of old encounters. Without dust and gas, none of this would happen. No new stars, no fresh light. A galaxy would slowly drift toward stillness. Instead, places like Andromeda are constantly recycling themselves. Gas collapses into stars. Stars spend millions or billions of years fusing lighter elements into heavier ones. In their old age, some blow off their outer layers in gentle winds. Others end in violent supernova explosions, throwing enriched material back into space. That debris cools, joins dust and gas again, and becomes part of the next generation of clouds. Each round adds more heavy elements to the mix. Carbon, oxygen, iron, silicon. Those are the same ingredients that later become rocks, oceans, atmospheres, and eventually things like plants and bones and thoughts. When we say Andromeda is immense, we often mean the width of its disk or the number of its stars. But it's also immense in this quieter way, in the depth of this ongoing cycle. In the fact that, for billions of years, it has been breathing in cold gas and breathing out starlight and enriched dust. Look at a high-resolution picture of Andromeda, and that breathing is written all over it. Bright star clusters beside dark dust lanes, smooth patches broken by cloudy, glowing regions. It's not just pretty, it is the visible sign of the galaxy's inner life. The contrast between brightness and shadow is not decoration. It is evidence that the galaxy is still active, still forming stars, still processing its own material, instead of coasting toward a silent end. We see something similar at home. The disk of the Milky Way is full of dust that blocks our view in some directions. There are parts of our own galaxy we cannot see in visible light, because dark clouds stand in the way. It's frustrating if you want a clear picture, but if we somehow stripped away all that dust, we would also be removing the raw material for future stars and planets. Clarity would come at the price of future possibility. So astronomers learn to work with the dust instead of against it. They look in infrared, in radio, in ultraviolet and X-rays. Each kind of light flows differently around dust and gas, revealing a different layer of the story. Andromeda, when seen this way, turns from a flat spiral into a multi-layered living system. Dust hides in one view and glows in another. Gas appears where stars are few. The galaxy becomes less like a picture and more like a breathing organism. The true scale of these clouds is hard to grasp. Some are tens of light years across. Some stretch hundreds. Inside them, small fragments collapse to form star clusters. A single cloud might give birth to thousands of stars over time. The parts that don't collapse drift on, reshaped by shock waves, gravity, and radiation, waiting for their moment in a later cycle. These clouds don't sit still. They move around the galaxy, swept along by its rotation, compressed as they pass through spiral arms, stirred by the gravity of nearby stars and the blast waves of supernovae. The result is a medium that is always shifting, always turbulent, but not random. There is enough order in the chaos for stars to keep forming in a more or less steady rhythm. In Andromeda, the arrangement of dust and gas into rings and arcs hints strongly at past drama. A smaller galaxy may have punched through the disk long ago, like a stone dropped into a pool. Waves of compression would have rippled outward, piling up dust and gas into curved bands. Wherever the material was compressed, new bursts of star formation would have followed. Those rings we see today are not just pretty patterns, they are the scars of that event, still visible, long after the collision itself is over. To read Andromeda's dust and gas is to read its memory. Stars tell you something about the ages and chemistry of the galaxy. Dust and gas tell you how it has been disturbed, how it has recovered, where it still has fuel left to burn in future generations of stars. This constant trade between stars and the medium around them explains how galaxies can remain active for billions of years. Stars give matter back, as well as light. Their winds and explosions refill the interstellar medium with enriched material. New stars form from that medium. Around those new stars, disks of dust and gas can gather and form planets. Those planets inherit the elements that were built in earlier stars. The cycle continues over and over, slow but relentless. If you think of Andromeda as breathing, it becomes easier to picture. The galaxy takes in gas, gathers it into dense clouds. That's the inhale. Then it exhales in the form of starlight and enriched material blown back into space. Each breath takes millions of years, but it is a rhythm, all the same. Not a human rhythm, not a heartbeat or a sigh, but a cosmic one. From far away, you see the broad result, glowing arms traced with dark lanes. Up close, you would see the moving details. Clouds collapsing, stars igniting, shells of gas expanding from old explosions, new dust forming out of cooled material. Every part of Andromeda's shape is influenced by where that dust and gas has gathered, where it has been used up, and where it is being pushed aside. As the future unfolds, this will continue only as long as there is gas left to use. One day, far ahead of us, Andromeda's gas reserves will run low. Star formation will slow to a trickle. The galaxy will grow quieter. No new bright blue clusters will form to light the arms. It will drift into an older, more subdued phase of its life. But that is not where it is now. Now, it is still breathing, still renewing, still mixing light and shadow into patterns that we can see from millions of light years away. So when we ask how big Andromeda really is, the answer is not just about how many light years its disk spans, or how many stars fill its spiral. It is also about the reach of the invisible material that threads through it, the dust and gas that extend beyond the bright starlight, that add mass without adding obvious glow, that shape what we can see and what we cannot. The immensity of Andromeda lives not only in its stars, but in this hidden medium that turns a static collection of suns into a living, evolving system. A galaxy that, on a timescale far beyond our own, is still quietly in the act of becoming. If you could peel back the layers of Andromeda, like the skins of an onion, you would pass the broad, faint halo of stars, then the long spiral arms, then the bright central bulge. You would move past rings of dust and swarms of stars packed so tightly together that the sky in every direction would glow, and still, you would not yet have reached the true center. At the very heart of Andromeda, there is something you cannot see, not because it is small, but because it is too intense to let light escape at all. It does not shine. It does not glow. It simply bends the world around it so strongly that light itself curves inward and never comes back out. This is Andromeda's supermassive black hole. The phrase sounds dramatic, and it is, but it can also be easy to misunderstand. People often imagine a black hole as a kind of cosmic drain, sucking everything nearby into oblivion. In reality, even a huge black hole does not hoover up the entire galaxy. It is more like an extreme anchor, a region where matter has collapsed into such a dense state that the rules we normally use for space and time start to warp. At the center of a black hole, our equations point toward a singularity, a place where density becomes so high that our current understanding breaks down. Around that interior lies the event horizon. You can think of it as an invisible boundary. Cross that boundary going inward, and nothing, not even light, can climb back out. To the outside universe, anything inside that surface is gone forever, its story cut off from our view. But just outside the event horizon, things are anything but quiet. Gas and dust spiral inward, forming a sort of whirlpool of matter. As they fall, they speed up. Friction heats them to extreme temperatures. They begin to emit fierce radiation. The black hole remains dark, but the space around it can blaze. In some galaxies, this makes the core shine so brightly that it outshines all the stars put together. Andromeda's black hole is enormous. Its mass is estimated at around 100 million times that of our Sun. Our own galaxy's central black hole, Sagittarius A, is already impressive at about 4 million solar masses. Andromeda's is about 25 times heavier than that. It is a giant among giants. With that much mass packed into such a small region, its gravity is not just a local detail. It shapes the way stars move throughout the central bulge. The innermost stars whip around it at tremendous speeds, like cars racing around a tight curve. If you watch those stars carefully and measure how fast they move, you can work backward and figure out how much invisible mass must be pulling on them. That is how astronomers know the black hole is there, even though they cannot see it directly. The stars near the center of Andromeda are moving too fast to be held in place by visible stars alone. Something heavy is sitting in the middle, quietly commanding the dance. What might surprise you is how calm that giant seems right now. In some galaxies, the central black hole is ravenous. It feeds on gas and dust at high rates, and as that material spirals inward, it releases staggering amounts of energy, sometimes blasting out jets that stretch far into space. These are called active galactic nuclei, or, at their most extreme, quasars. Andromeda's black hole is currently not in that kind of mood. It is relatively quiet. It is not swallowing large amounts of material. It gives off only faint, high-energy radiation. For now, it is more like a huge weight resting at the bottom of a deep well. Its presence is undeniable, but it is not roaring. That quietness is lucky for us. A highly active black hole in a nearby galaxy would flood space with intense radiation. Instead, Andromeda's core sits in a kind of cosmic low-power mode. The question of how such a massive black hole came to be is still open. Did it start small, born from the collapse of a massive early star, and then slowly gain weight over billions of years as gas and stars fell in? Or did it grow quickly in the young universe, perhaps through a series of mergers with other black holes? Andromeda itself has been anything but lonely. It has swallowed smaller galaxies over time. Many of those galaxies likely had their own central black holes. When their stars were stripped and mixed into Andromeda's halo and bulge, their black holes would have sunk toward the center, spiraling inward and merging. Each merger would have shaken the core with energy, briefly lighting it up before the new, larger black hole settled again. So when you think about Andromeda's central black hole, you can picture not just a single object, but a history of many cores blended together. A record of past collisions, all condensed into one extreme point. What makes this central object so important is not only its mass, but its role. It is not just an oddity sitting in the middle. It is part of what makes Andromeda Andromeda. The motions of stars in the bulge, the behavior of nearby gas, the structure of the inner galaxy, all of these are shaped by the deep, unseen gravity well at the center. Without that anchor, the pattern of orbits would be different. The heart of the galaxy wouldn't beat in quite the same way. To imagine the environment close to this black hole is to step into a place where our intuition fails. Gravity there is strong enough to bend, not just the paths of planets or stars, but the path of light itself. Space doesn't feel flat. It curves inward. Time behaves strangely. If you could hover safely in a stable orbit, very close to the event horizon, far enough not to fall in, but close enough to feel that immense pull, time for you would slow down compared to the rest of the universe. You would see the galaxy outside aging faster than your own experience. This sounds like fantasy, but it is a real prediction of general relativity, the theory that describes how mass bends space and time. Gas that strays too close is heated to millions of degrees as it spirals inward. It glows in X-rays, a kind of light our eyes cannot detect, but our telescopes can. Observations in those high energies have revealed faint signals from Andromeda's core. Not the blazing beacon of an active quasar, but a quiet flicker that confirms something extreme is there, influencing matter on the brink of no return. One day, instruments similar to the Event Horizon Telescope, which has imaged the surroundings of black holes in other galaxies, may be able to resolve the region around Andromeda's black hole as well. For now, we see it mostly through movement and faint whispers of radiation. Its face is still hidden. Its shadow is inferred rather than directly drawn. This black hole is not just important for the present. It matters for Andromeda's future as well. Billions of years from now, When Andromeda and the Milky Way finally collide and merge, their central black holes will not stay strangers. They will feel each other's gravity across the merging cores, spiral inward together, and eventually fuse into one even larger black hole, hundreds of millions of solar masses in weight. As they merge, they will send ripples through space-time itself. Gravitational waves will spread outward, like ripples on a pond, carrying away energy. No one we know will be alive to witness it. The Earth as we know it may not even exist, but the event will still happen, a quiet climax in the long story of our local group of galaxies. All of this, the growth, the silence, the future merger, is contained in that faint blur you can see in the night sky. When you stand outside and pick out Andromeda, you are looking at a galaxy whose center hides an object so extreme that our usual language for size and density almost falls apart. 100 million suns worth of mass crushed into a region so small that no light escapes. And yet, around this extreme heart is a crowded neighborhood. Dense clusters of stars whip around in tight orbits. Some of them will occasionally get too close, their paths twisted inward until they cross the event horizon and vanish from our view forever. Others will be flung out instead, slingshot by the black hole's gravity and hurled into the wider galaxy at enormous speeds. The core is busy, even if the black hole itself is quiet in terms of radiation. To really understand Andromeda, you have to include this hidden heart in the picture. The spiral arms, the dust rings, the halo of stars, the satellites and streams. These are the wide, visible parts of the story. The black hole is the invisible punctuation mark at the center. It adds weight, it shapes the rhythm. It reminds us that the galaxy's immensity is not just spread out across space in stars and gas, but also concentrated into a single, extraordinary point where the familiar rules bend. When you next imagine Andromeda, you can picture both scales at once. The grand sweep of its arms across hundreds of thousands of light years, and at the center, a region from which no light returns. A galaxy made of countless shining stars, all turning, ultimately around an unseen core, where space and time themselves are pulled into a different shape. When you picture Andromeda, it's easy to imagine it as a single, grand thing, a mighty spiral hanging alone in the dark. Arms unfold, center glowing. A solitary beacon in the black. But galaxies that large almost never live alone. Just like our Milky Way has its own little companions, the large and small Magellanic Clouds, Andromeda too is surrounded by a crowd. A faint, quiet crowd of smaller galaxies that orbit it over millions of years. They don't look impressive at first glance. Many are dim, blurry, easy to miss even in a telescope. And yet they are bound to Andromeda by gravity, moving around it like distant lanterns circling a giant campfire. Together, they form a system. A family of galaxies, with Andromeda as the central elder. So when we ask how large Andromeda truly is, we can't stop at its bright disk or its halo of stars. Its real reach includes the company it keeps. Two of Andromeda's companions stand out as the most noticeable. They're known as M32 and M110. Both are elliptical galaxies, small compared to Andromeda, but still galaxies in their own right. M32 is like a tiny, overpacked city of stars. Compact and dense, its stars are crammed close together, giving it a surprisingly bright appearance for its size. Many astronomers think it used to be bigger, with outer layers that were slowly peeled away by Andromeda's gravity. What we see now may be its stripped-down core, the tough center that survived. M110 is different. It's softer, more spread out, its light more diffuse. In deep images, you can see hints of streams and disturbances, as if it has been tugged and teased by Andromeda over time. These scars suggest that M110 too has been reshaped by living so close to a giant. Both of them sit near Andromeda's main disk, close enough to be picked out as faint patches in a small telescope. They're like two quiet companions walking beside a much taller figure, noticeable only if you look closely. But the family doesn't end there. Beyond M32 and M110 are dozens of smaller dwarf galaxies. Many are so faint that they went completely unnoticed until the last few decades. Only with careful sky surveys, designed to search for tiny clumps of stars against the darkness, did they finally reveal themselves. Some of these dwarfs are irregular little clouds of light, like someone smudged a thumb across the stars. Others are more spheroidal, smooth and ghostly, almost like faded memories hanging in space. Each one contains millions or tens of millions of stars. That might sound small beside Andromeda's trillion stars, but compared to anything on human scales, each dwarf is still vast beyond imagination. The relationship between Andromeda and these satellites is not calm and static. Gravity is always working, always pulling, always reshaping. Some of the smaller galaxies are being slowly torn apart. As they orbit, Andromeda's gravity stretches them, pulling stars out into long, delicate streams that wrap around the main galaxy. In very deep images, these streams appear as faint arcs of light, looping through the halo. They are the trails left by galaxies that came too close and were slowly digested. This is how Andromeda grows. Over billions of years, it has fed on its neighbors, pulling them apart and folding their stars into its own outskirts. Our Milky Way is doing the same thing right now to the Sagittarius dwarf galaxy, pulling it into long streams that wrap around us. But Andromeda, being larger and more massive, likely has an even longer history of such meals. Its halo is full of star streams and shells, fossils of past galaxies. Each arc is a record of something that once traveled alone, and now lives as part of something larger. By studying these satellites, astronomers learn about the environment in which Andromeda exists. How many dwarfs are there? Where do they sit? How are they moving? How distorted are they? These details feed into our understanding of dark matter. Theories suggest that big galaxies like Andromeda and the Milky Way should be wrapped in large halos of dark matter and surrounded by many smaller galaxies, each with its own mini-halo. The number and distribution of satellites around Andromeda help test that idea. If there are fewer dwarfs than expected, or if they're arranged in unusual ways, it challenges our models and forces us to refine them. So the satellites don't just tell us about Andromeda, they tell us about the invisible structure of the universe itself. For us, they also change how we think about Andromeda's size. It isn't just a disk 220,000 light-years across. That's only the bright part. Its true reach extends out into the space where its satellites orbit, across millions of light-years. Its gravity reigns over not just its own stars, but the stars in dozens of other galaxies that circle around it. When we say Andromeda is immense, we are really talking about this whole domain, this entire gravitational kingdom. There is also a story in the variety of these companion galaxies. Not all of them look or behave the same. Some are still gas-rich, irregular galaxies where new stars are forming. These are the lively ones, with clouds of hydrogen, pockets of starbirth, and younger populations. Others are gas-poor and quiet, made almost entirely of old stars. No bright nebulae, no new clusters, just a faded glow. The difference often depends on how close they come to Andromeda. Satellites that stray too near the giant can lose their gas. Tides pull on them. The hot halo around Andromeda can strip their remaining gas away. Without that gas, star formation stops. They turn into dim relics, cangent star cities where the lights are slowly going out. Dwarfs that live farther out, on wider orbits, can keep more of their gas. They can continue forming new stars, staying active for longer. In this way, Andromeda is not just a passive central figure. It is a powerful neighbor that can decide which of its companions remain vibrant and which fade into quiet, fossil galaxies. Some of the faintest satellites are so diffuse and dim that even big telescopes struggle to see them. Their stars are spread thin, so their surface brightness is barely above the darkness of the sky itself. To find them, astronomers look for tiny overdensities. Little statistical bumps, where a subtle cluster of stars moves together. Finding these ultra-faint dwarfs has shown that Andromeda's family is bigger and more varied than we once realized. The galaxy is not just a shining disk, with a couple of companions. It is the center of a complex layered community. The satellites don't just orbit and look pretty. They help shape Andromeda itself. As they move around it, they deposit stars and dark matter into the main halo. Their gravitational pulls can tug on Andromeda's disk, creating asymmetries, rings, or warps in the spiral. Over time, their repeated passes can stir the galaxy's structure, triggering waves of star formation in some regions, thinning others out. So, Andromeda is not a finished sculpture in space. It is a work in progress. A galaxy being slowly recarved by the company it keeps. If you imagine drifting outward from Andromeda's bright core, past its spiral arms and dust lanes, you'd eventually leave the main disk behind. The glow would thin, the stars would spread out. And then, one by one, you'd start to encounter its satellites, a compact little ellipse off to one side, shining more brightly than its size suggests. A faint smudge hanging in the dark like a small, shy cloud, a barely perceptible cluster of stars that only resolves itself when you get very close. Each of these would have its own history. Maybe it once fell in from farther away. Maybe it's already being stretched apart. Maybe it has already given some of its stars to Andromeda and is on its way to becoming nothing more than a stream. But no matter their individual stories, all of them would have one thing in common. They are held in Andromeda's grip. They move through its gravitational field. They belong to its wider system. A single dwarf galaxy with a few million stars would dwarf the scale of anything we can build or touch. If we could place such a dwarf next to our solar system, it would feel impossibly large. Far too big to ever cross, far too full of stars to count. And yet, next to Andromeda, that same dwarf is tiny, a whisper of light orbiting a shout. The contrast is striking. A giant galaxy like Andromeda is the heavyweight, the dominant mass. Its satellites are the small but revealing details, the supporting cast that helps you understand the main character's true size. To really study Andromeda, then, is to study all of this together. Not just its bright core and sweeping arms, but its halo, its streams, its satellites, and the space in which they all move. It is not a single object, but a network. A web of relationships shaped by gravity over billions of years. Andromeda's size is not only the number of light years across its disk. It is the volume of space where its gravity rules. It is the company that moves in its shadow. It is the quiet family of galaxies revolving around it. Each one a reminder that even on the largest scales we know, nothing truly exists alone. It is not only wide in light years, it is deep in years of light. Its immensity stretches not just across space, but across time itself. When you look at Andromeda, you are not simply tracing the length of its arms or the span of its halo. You are touching one thin slice of its history, one luminous page in a book that began long before us and will continue long after. In that sense, the galaxy is not a single thing. It is a sequence of selves. There is the Andromeda that existed when those photons left. Its stars arranged just so, its clusters at certain stages, its gas clouds poised between collapse and creation. There is the Andromeda of tonight, 2.5 million years further along, already changed in ways we can't yet see. And there is the Andromeda of the future, the one that will collide with our own galaxy, merge, and become something new. All of these are Andromeda. We meet only one version, delayed by distance. If you imagine the galaxy's life as a film, each frame lasting millions of years, we currently see only a single, still image, beautiful, detailed, but incomplete. As time passes, different frames will reach us. The Andromeda your distant descendants might observe, if they look up and remember to search the sky, will be slightly different from the one you see now. New stars will have appeared, old ones will have vanished, and subtle shifts in its structure will have taken place. The universe does not rush. Its changes are real but slow. So slow that for us they feel like stillness. And yet, the light never stops arriving. Every night, new photons fall through our atmosphere, slip past clouds and city glow, and end their journey on mountains, on oceans, on rooftops, on retinas. The stream is constant, a river of history we are always standing inside, whether we notice it or not. If you lie back and imagine those photons as travelers, you might picture them leaving their star in Andromeda before there were mammoths, before there were written languages, before any human ever carved a symbol into stone. They crossed a universe that on large scales barely changed along their way. Galaxies drifted, clusters moved, but nothing stopped them. No one saw them until tonight, when a few of them by chance met you. That's part of what makes this so quietly personal. The cosmos can feel abstract and distant when it's written in numbers, millions of light years, billions of stars, trillions of worlds. But a photon is small, specific, singular. It followed one path to one point. It doesn't know who you are, of course, but the fact remains, its long journey ends in your eye, in your moment, in this breath. So when we talk about how big Andromeda is, we're not only talking about how far it spreads across the sky or how many stars it contains. We're talking about how far back it reaches into the past we can see. We're talking about the thickness of the history it delivers every time it rises over the horizon. Its size is spatial. Its size is temporal. Its size is also emotional. The distance it pulls our thoughts from daily scale into cosmic scale, because in the end, this time-shifted light does something gentle to the mind. It reminds us that right now, while you are listening, while your day's concerns slowly soften at the edges, the universe is older and larger than anything on your to-do list. That doesn't make your life smaller in value. It just gives it a frame, a wider backdrop in which your worries can breathe a little. You are here for a brief span of years. Andromeda has been shining for billions. Yet, for this fleeting overlap, you and the galaxy meet. You bring the questions, it brings the light, and together, in that meeting, the idea of how big begins to shift from just numbers to something you can feel, a quiet awe, a long perspective, a sense of resting beside a story that started long before you and will continue long after, but allows you kindly to share one small luminous chapter. Every time you look up at the sky, you are not seeing the universe as it is. You are seeing it as it was. Light is fast, but it is not instant. It has to cross the distance between where it was made and where you are now. That travel takes time. So every star, every galaxy you see, is already a memory by the time its light reaches you. For nearby things, that delay is tiny. The moon feels close, and in a way it is. Its light takes just a little more than a second to get here. The sun feels like our immediate neighbor, but its light is already 8 minutes old when it touches your skin. You never see the sun right now. You always see it as it was 8 minutes ago. With Andromeda, that quiet delay becomes something else entirely. The light from that faint blur has been traveling for around 2.5 million years. When you see Andromeda tonight, you are not seeing the galaxy as it exists in this moment. You are seeing it as it was before humans had cities, or stories written down, or even a word for galaxy. To sit with that thought is to realize that looking is also a kind of time travel. The photons entering your eyes from Andromeda began their journey long before our species settled into what we now call history. They set out when early humans were shaping rough stone tools, when giant sheets of ice lay across huge parts of the planet, when Earth's climate, animals, and landscapes were in a chapter we can only guess at. And yet those same particles of light have been crossing space all that time, only to end their journey quietly in your vision tonight. This is not a special trick reserved just for Andromeda. In astronomy, it is simply how things are. Everything we see in the sky is already part of the past. The farther away something is, the older the light we receive. With Andromeda, the delay happens to be in a strange sweet spot. 2.5 million years is far beyond a human lifetime, far beyond the rise and fall of whole civilizations, but it is still close enough that the galaxy is visible to your eyes as a pale patch in the dark. Most galaxies we study through telescopes are so far away that their light left long before humans existed at all. For them, we are reading chapters written billions of years ago. Andromeda's light is ancient, but it still brushes against the story of our own species. The glow you see from Andromeda is not the voice of a single star. It is a blend from billions of suns, each at its own point in life. Some of those stars have already burned out. Some have ended in huge explosions. Some have gently faded. But the light they sent out back then kept going, carrying a record of what they were at that moment 2.5 million years ago. So the Andromeda you see is like a fossil made of light. A frozen frame in a film that is still playing, but with the latest scenes hidden from us. Astronomers lean on this built-in delay. They use it not just to study Andromeda, but to read the history of the universe itself. By looking at more distant galaxies, they are looking deeper into the past. The most remote objects we can detect are seen as they were not long after the universe first began to form stars and galaxies. The sky becomes a kind of library. Each distance is a different shelf. Each shelf holds a different time. Andromeda is on one of the nearer shelves, close enough that it feels like a neighbor. Far enough that it still carries us past all of human history and into a much older world. When you see it, you are connecting with a time that has vanished in every way, except for this trail of light, still arriving. There is something humbling in remembering that what we see tonight is not what Andromeda looks like tonight. Its stars have shifted on their orbits. Clusters have changed. New stars have ignited. Others have died. Perhaps supernovae have flared and faded in the time since that light first left. The galaxy has continued living its quiet, slow life while we watch only an earlier version, like an old photograph that never updates. If we could somehow switch to a true real-time view, the changes would probably look delicate to our eyes, but in meaning, they would be huge. We would be watching millions of years of evolution catch up all at once. Instead, we are always behind, always looking back. Not because our tools are bad, but because this is the way the universe works when light has to travel. The light that reaches us is not all the same kind. Our eyes see just one narrow slice. In that slice, we see stars and the bright core and hints of the spiral arms. But there are other kinds of light, other colors our eyes cannot detect. Some light is longer and softer, carrying warmth rather than visible glow. That kind of light, which we call infrared, slips through dust and shows us cooler regions where new stars are still in the cradle. Some light is more energetic, beyond violet, coming from very hot young stars. That light highlights places where star birth is recent and fierce. Even more energetic forms of light arrive from violent events, like exploding stars or matter swirling near the central black hole. Each type of light is like a different layer of the story. Put together, they make a fuller picture of Andromeda's life than any single kind could offer alone. To our naked eyes, Andromeda's light is barely there. A soft, ghost-like smear that you might miss if you are not looking for it. But a telescope, especially one that can take long, patient exposures, treats that faintness differently. It gathers those ancient photons for minutes or hours, steadily collecting what our eyes lose. The image that appears is suddenly rich. Spiral arms sharpen. Dust lanes become clear, dark threads. Clusters of stars step out of the haze. All that structure was always in the light. We just needed a way to hold on to enough of it at once. Every photograph of Andromeda you have ever seen is built from light that spent millions of years crossing the space between galaxies. Each tiny dot in the image, each pixel, is a count of those travelers. A record of ancient light finally coming to rest. In that way, the galaxy is both unimaginably far and strangely close. You do not need to go there to know something about it. It comes to you. Continuously, as a quiet river of photons falling on the planet, night after night. Thinking about light this way ties directly into the idea of cosmic history. When you look at Andromeda, you are not just seeing a place. You are seeing a moment within its long life. 2.5 million years sounds enormous to us. But for a galaxy, it is just a blink. Andromeda was already ancient when that light set out. It will still be there long after tonight. The light you see is one frame of a movie that has been running for billions of years. It is easy to forget that the photons arriving tonight are not the same ones that arrived last night. Those already finished their journey. These are new ones, just as old, just as patient. Every second, more of them reach us. A steady rain of old messages. To lie beneath the stars and gaze at Andromeda is to bathe in that stream of history. You let it move over you. You feel, even for a brief moment, that you are part of something that stretches far beyond the scale of human time. There is something quietly personal in all of this. When you look at Andromeda, the photons that enter your eyes end their long voyage with you. No one else will ever receive those exact particles of light in that exact way. Others will see the galaxy. Others will catch their own photons, but the particular ones that traveled for millions of years to meet you finish their path in your vision alone. In that sense, the connection is intimate. The galaxy is enormous, but the way its light arrives is one photon at a time. One person at a time, one moment at a time. That intimacy does not shrink its immensity. It makes it feel more real. Something so vast, so old, can still reach you directly, can still end up inside your eyes and your thoughts. It is a bridge between your human scale and the scale of galaxies. You are not outside the universe, looking in. You are inside it, made of the same matter, listening to its messages, carried by light. So, when we talk about how big Andromeda is, we are not just talking about how wide it is across space. We are also talking about how deep it runs through time. It is large in light years, yes. But it is also large in years of light, in the history it holds in its glow. Its true size is not only measured from edge to edge, but from past to present in the river of photons still arriving, one ancient shimmer at a time. It is easy to talk about galaxies with numbers. We can say how wide they are in light years. We can list star counts in the hundreds of billions. We can write down masses in units of suns. All of that is useful, but after a while it raises a quieter question. What does any of this actually mean for us? Down here, Earth already feels huge. You can walk for hours and never leave a city. You can fly for many hours and still be on the same continent. Crossing an ocean takes most of a day. If you travel around the world, it feels like a big achievement. Our planet is large on the scale of a human body. It feels endless when you look out over a sea or a desert. Step out one level, and our solar system makes even Earth seem small. The distance from the Earth to the Sun is about 150 million kilometers. Light, which moves faster than anything else we know, needs about 8 minutes to cross that gap. A normal airplane would have to fly non-stop for decades to get there. Already, that is beyond normal experience. We cannot feel those distances in our bones. We only meet them in diagrams and numbers. Then we put that whole system next to a galaxy like Andromeda. Suddenly, even 150 million kilometers vanish. The 2.5 million light years between us and Andromeda make the space from Earth to Sun look like a step across a puddle. The entire solar system shrinks to a tiny speck. Our planet shrinks to a dust grain inside that speck. Our own bodies barely register at all. This can feel uncomfortable. When you realize just how small you are, there can be a sense of being washed away. Some people look at those scales and feel that human life must be meaningless in comparison. How can anything we do matter against such immensity? But small does not mean empty of meaning. We never judge the value of something only by its size. A wildflower at the edge of a cliff is tiny next to the mountain, but it still moves us. A child's laugh weighs almost nothing, but it can change a whole room. A thought has no length or width, but it can reshape a life. Value lives on a different scale. Human life has its own kind of size, not in kilometers or light years, but in experience, in awareness, in the ability to notice. The Andromeda Galaxy exists on its vast scale. We exist on ours. The connection between the two lies in the fact that we can look up and wonder about it at all. Think about what our species has done. We have taken that faint blur in the sky and turned it into questions. We have built instruments to collect its light. We have written equations to describe its motions. We have sent machines into space, aimed telescopes above the atmosphere, stored images on tiny chips. From our small, fragile world, we reach mentally out to a galaxy millions of light years away and give it a name. That ability to reach with the mind is extraordinary in itself. It also helps to remember where we came from. The atoms in your body are not separate from the cosmos. The carbon in your muscles, the oxygen in your lungs, the iron in your blood, the calcium in your bones, all of those were made inside stars. Some came from stars that lived and died before the sun was born. Those stars fused light elements into heavy ones and then scattered them in explosions. Clouds of that enriched gas later collapsed and formed new stars, new planets, and eventually us. So the vastness is not just out there, it is inside you. You are literally built from the same materials that light up Andromeda. In that sense, human scale and galactic scale are not enemies. They are two expressions of the same universe. The galaxy shows what matter does across hundreds of thousands of light years. You show what matter does when it organizes into a nervous system that can feel, remember, and wonder. Time has its own version of this contrast. Our lives are measured in decades. Long friendships might last half a century. A building might stand for a few hundred years. Civilizations rise and fall over thousands of years. That already feels ancient to us. Now place that next to Andromeda's time. Its light takes millions of years to arrive. Its stars can live for billions of years. The black hole at its center has existed for more than 10 billion years. Those spans are enormous, but they do not make ours disappear. They simply frame them. Our lives become brief notes in a much longer piece of music. Short, yes, but still part of the melody. And the human scale lets us make sense of the large scale in a special way. 1 trillion stars by itself is just a number. But think of one star you know well. The sun. Think of the warmth on your skin on a clear day. Think of the way plants lean toward it and the way its light shapes every day of your life. Then imagine not one sun, but countless suns, each with its own planets, its own skies. Suddenly, trillion stars is not just a statistic, it becomes a field of possibilities. The vastness turns into a stage for curiosity and wonder. In this way, human scale is not opposed to cosmic scale. It is the lens through which cosmic scale becomes meaningful at all. Without a mind to think about it, Andromeda is simply there. With a mind to notice, it becomes a source of awe. Picture yourself standing under a dark sky. You are just a body a couple of meters tall. You stand on a planet about 12,000 kilometers wide. That planet orbits a star. That star is one of hundreds of billions in the Milky Way. And right there, above the horizon, you are looking at another galaxy with perhaps 1 trillion stars of its own. You, tiny as you are physically present in that meeting between scales. In that moment, the universe is looking at itself through your eyes. People have felt this for a very long time. Long before we knew what galaxies were, stargazers felt something deep when they saw the Milky Way arching overhead, when they noticed a pale blur in the direction we now call Andromeda. They did not know its size or distance. But the feeling of being very small under a very large sky was already there. Today we have more numbers, more explanations. The emotional experience is the same. We now call that feeling the sublime, sometimes. A mixture of awe and humility, when you touch something far beyond what you can fully grasp. Science gives us tools to measure and describe that vastness. It can tell us how many stars, how far, how massive, but the experience of standing under the sky, breathing cool air, and letting that knowledge sink in is still personal. It belongs to each person who feels it. In that sense, science and feeling are not separate. The measurements deepen the wonder rather than replace it. Seeing our smallness also has a practical side. When we understand how big galaxies are, we see how delicate our own world is. The Earth is a thin layer of rock and air and water wrapped around a small planet. It is not a fortress. It is more like a fragile bubble in a huge, dark sea. Galaxies will go on for billions of years, long after our sun has burned out. But whether life on Earth continues for a long time or ends sooner depends on what we do, how we treat our climate, how we share our resources, how we use the knowledge we've gained. The cosmic backdrop does not make these choices less important. It makes them more precious. We realize that this small, living world is rare and worth protecting. Our sense of scale also colors how we think about the future of Andromeda and the Milky Way. We know that in about 4 billion years, the two galaxies will begin to merge. By that time, the sun will be nearing the end of its own life. Earth may no longer be a safe place for life as we know it. Humans, at least in our current form, will almost certainly be gone. Maybe new beings will exist. Maybe they will watch the sky and see Andromeda swell and stretch and finally blend with the Milky Way into a new, larger galaxy. For the galaxies, the merger will be an ordinary event. Gravity, doing what gravity does. For a conscious mind, it is a story, a future sky, a picture we can imagine even if we will never be there. That is what the human scale does. It turns raw events into narratives. It lets us care about a collision that will happen billions of years from now. It allows us to connect our brief moment to something far beyond our duration. So when we place ourselves against a vastness, the real task is not to compete. It is to recognize the relationship. Galaxies are immense, but our minds can stretch toward that immensity. Our lives are short, but they unfold inside a universe that goes on. Our bodies are small, but they are made of the same atoms that shine in distant stars. The human scale and the galactic scale are two different ways the universe expresses itself. One through swirling arms of stars, one through a heartbeat and a wandering thought. As we keep exploring Andromeda in our minds, it helps to hold both truths at once. We are small, yes, but not meaningless. We are brief, yes, but not without value. We do not stand at the center of the galaxy. We stand within it, as observers and participants. As beings who can look up at that faint blur and quietly ask, what does this mean? That simple act of asking is its own kind of vastness, a reach of the mind that goes beyond our height, beyond our years, and leans gently into the scale of galaxies. If you could go back thousands of years and stand beside someone under a clear night sky, Andromeda would still be there, the same faint blur, the same soft patch of light, but to them, it would not be a galaxy. There was no such word yet, no idea of island universes or spirals of stars. It was simply a curious mark in the darkness. Still, they noticed it. They folded it into their sky. They gave it a place among the constellations. They drew maps in their minds and, later, on parchment. Even without knowing what it was, they thought it was worth remembering. The first time we can clearly see Andromeda written down is in the 10th century. A Persian astronomer named Abd al-Rahman al-Sufi sat with the night sky long before streetlights and satellites. In his Book of Fixed Stars, finished in the year Dino 64, he described a little cloud in the constellation we now call Andromeda. He carefully noted where it sat among the brighter stars. He called it the little cloud, not a galaxy, not a spiral, just a small, misty patch. Of course, he was not the first human to see it. People before him must have noticed that blur again and again over countless nights. But his description is the oldest one we still have in writing. Through his words, the faint patch of light stepped into recorded history and stayed there. Long before that, the Greeks had already traced a pattern of stars in that part of the sky. They imagined a princess chained to a rock, waiting to be rescued. That became the constellation of Andromeda. Bright stars like Alpheratz marked the pattern. Inside that pattern, quiet and easy to miss, lay the blur we now recognize as a galaxy. We do not have surviving Greek texts that clearly say, "Here is a little cloud," but it is hard to believe that careful sky watchers under truly dark skies never saw it. The light was there. The eyes were there. The myths were there. The written record has just faded. Other cultures also kept their own star stories. Indigenous peoples across the world looked up and saw paths, animals, boats, camps, and rivers traced in the Milky Way. They used the sky as a calendar, a compass, a storybook. It is easy to imagine that in some of those traditions, the faint smudge of Andromeda earned a name and a role, even if those names never reached our books. The blur was part of many skies, long before it became part of formal astronomy. By the Middle Ages, al-Sufi's little cloud had traveled through languages. His work was copied, translated, and studied. Astronomers in the Islamic world, and then in Europe, used his catalogues as guides. Through this chain of translation, Andromeda's blur found its way onto European star maps. There, it was usually filed under one simple category, nebula. Back then, nebula just meant a fuzzy object, a cloud, a patch, anything that was not a sharp pinprick, like a star. There was no deeper meaning hidden in the word. It simply said, "This thing looks blurry." For centuries, Andromeda stayed in that box, something to note, to draw, to label, but not yet to understand. It sat on the page as a mystery, with a neat little name. Then came the telescope. In the early 16,000s, people started turning lenses and mirrors toward the sky. Objects that once were tiny and vague suddenly grew larger and sharper. In 1612, a German astronomer named Simon Marius pointed a telescope at the Andromeda Nebula. He saw a faint, cloud-like glow, broader than the eye alone could see. He wrote about it as a soft extended light, confirming that the little cloud was indeed more than just a single star. Galileo may have glimpsed it too, though we are not completely sure. Even with these early instruments, though, Andromeda was still classed as a nebula inside our own Milky Way. A strange patch, yes, but still assumed to be part of our own star system. As the centuries passed, more and more careful observers kept adding Andromeda to their lists. Charles Messier, a French astronomer hunting for comets, got tired of being fooled by fuzzy objects that were not comets at all. So he made a catalogue of these things to ignore when comet hunting. Andromeda made the list as Messier 31 or M31. Ironically, his list of distractions later became one of the most famous guides to deep sky objects. The little cloud had now become a numbered entry. William Herschel, who discovered Uranus, also studied Andromeda. He noticed its bright central core and its faint, extended regions. Some astronomers began to wonder whether these nebulae might actually be huge systems of stars far beyond our own. They called them island universes, but this idea did not win easily. The common belief was that the Milky Way was the entire universe. Everything we saw, including Andromeda, was assumed to sit inside our one great star system. By the early 1900s, the question had sharpened into a real argument. What were spiral nebulae like Andromeda? Were they baby star systems forming inside the Milky Way, or vast, separate star cities far beyond it? Astronomers Harlow Shapley and Heber Curtis became two of the main voices on either side. Their disagreement led to what is now called the Great Debate in 1920, held in Washington, D.C. At the heart of it was a simple but profound question. Is Andromeda part of our galaxy, or is it another galaxy altogether? The answer arrived only a few years later. Edwin Hubble, working at Mount Wilson Observatory with the giant 100-inch Hooker telescope, studied Andromeda in detail. He found a special kind of star within it, called a variable star, whose brightness changes in a way that reveals its true power. By measuring how bright those stars appeared from Earth and how they pulsed, he could work out their distance. What he found was stunning. They were far too distant to be inside the Milky Way. Andromeda was not a small cloud down the street. It was a galaxy in its own right, a separate island of stars, millions of light years away. In that moment, the universe grew. The Milky Way stopped being the whole story and became one galaxy among many. Andromeda became our nearest large neighbor, not just a fuzzy mark in our backyard. The little cloud had turned out to be an entire galaxy. Looking back, it is striking how long humanity lived with Andromeda as nothing more than a blur. For about 1,000 years after Al-Sufi wrote of his little cloud, it stayed mysterious. Only in the last century did we finally understand what we were really looking at. The galaxy did not change. Its stars did not suddenly appear. What changed was us. Our tools sharpened, our ideas stretched. We learned to question the assumption that the Milky Way was everything. Even the names tell this story. First, Little Cloud, then Nebula, then Messier 31. Finally, Andromeda Galaxy. Each label marks a step in our understanding, from a vague smudge to a catalogue entry to a recognized galaxy. Today we often just say Andromeda, but hidden inside that one word are centuries of guesses, arguments, and discoveries. The fact that it was ever noticed at all says something warm about humans. Andromeda is faint. It is easy to miss. Yet again and again, under truly dark skies, people saw it. They wondered about it. They folded it into their maps, into their myths, into their charts. They held on to it and passed it forward across generations, across cultures, across languages. By the time the right telescope and the right person came along, the target was already waiting, marked on the sky. Without that long chain of attention, Hubble might not have known exactly where to look or what question to ask. The faint blur near a princess in the sky became the key to unlocking the size of the universe. So when you look at Andromeda now, you are not just looking outward into space. You are also looking backward into time, into the history of human eyes staring at that same blur. You are standing in a very long line of sky watchers, from storytellers around ancient fires, to scholars working by lamplight, to astronomers at giant domes. To see Andromeda is to quietly step into that line, to notice, to name in your own mind, and to keep the wondering going. If you were standing under a truly dark sky, far from any town or road or screen, Andromeda would still look almost shy. Just a soft smear of light, barely there, right on the edge of what your eyes can notice. For thousands of years, that was the only version of Andromeda that humans could see. A little cloud, a blur in the night. No arms, no structure. Just a small, gentle, mistake-looking thing among the stars. Then we started building glass. We learned how to polish lenses. We learned how to shape mirrors. The telescope was born, and that tiny blur began to change. What once looked like a ghost spot slowly unfolded into something with detail. Not just a patch, but a pattern. Not just a glow, but a system. In the 1920s, when Edwin Hubble turned one of the largest telescopes of his time toward Andromeda, he could do something no one had done before. He could pick out individual stars inside that blur. Tiny points separated from the haze. That simple act, seeing single stars instead of a featureless cloud, was what proved Andromeda was not a cloud in our own galaxy at all, but another galaxy entirely. An island of stars all its own. Since then, our tools have grown almost beyond what Hubble could have imagined. we put telescopes on mountaintops. Then we put one above the atmosphere, orbiting Earth, staring into space with no air to blur its view. The Hubble Space Telescope has taken some of the sharpest images of Andromeda ever made. In those images, millions of stars are resolved as individual points. The spiral arms are not just smooth curves, they are crowded streets of suns. In 2015, astronomers stitched together a huge mosaic of Andromeda using Hubble's data. It was so detailed that it contained about 1.5 billion pixels. Zooming in feels like flying over a city at night, where every pixel is another star. For the first time, the size of Andromeda stopped being just numbers and started to feel like something your eyes could almost grasp. But visible light is only one way to look. Our eyes are tuned to a very particular slice of the spectrum. Modern telescopes stretch that slice in both directions. When we look in infrared, with instruments like those flown on space telescopes, Andromeda changes again. The bright stars fade a little, and the dust becomes the main actor. Dust that looks dark in ordinary pictures glows warmly in infrared. Rings and arcs appear, tracing hidden structures in the galaxy. These shapes likely formed when Andromeda interacted with smaller companion galaxies, its disk rippling like water after a stone is dropped. In ordinary light, those ripples are almost invisible. In infrared, they stand out clearly, showing where waves of star formation were kicked off by gravity. In ultraviolet light, a different story appears. This kind of light comes from very young, very hot stars. Telescopes that see in ultraviolet highlight patches where new clusters are forming right now. The old, cooler stars fade into the background. The youngest parts of the galaxy flare into view. Infrared shows the raw material. Ultraviolet shows the newborn stars. Together, they sketch out the cycle of gas collapsing and stars lighting up. Then there are X-rays. These do not come from calm stars at all, but from violence. Exploded stars leave behind hot, expanding shells of gas that glow in X-rays. Matter falling onto compact objects like dense stars, or the big black hole at the center, can heat up to such extreme temperatures that it shines in high-energy light. X-ray telescopes show Andromeda as a network of hotspots and bubbles. They reveal the scars of supernovae and a quiet feeding of the central black hole. The galaxy, which looked peaceful as a faint blur, turns out to be full of quiet explosions and extreme physics. Radio telescopes add yet another layer. By tuning to a specific wavelength emitted by neutral hydrogen, the most common gas in the universe, astronomers can map where that gas lies in Andromeda. Those radio maps show that gas stretches far beyond the bright disk. You see invisible light. The galaxy is larger in hydrogen than it is in starlight. By measuring how that gas moves, we also discover something odd. The outer parts of Andromeda spin too fast to be held together by visible matter alone. This is one of the clues that dark matter is there. Something unseen, adding mass and holding the galaxy together. The real magic happens when we stack all these views: optical, infrared, ultraviolet, X-ray, radio. Each one reveals different structures and processes. When astronomers combine them, Andromeda stops being a flat picture and becomes a layered story, a place where stars are born, live, and die. Where dust is both a hiding veil and a nursery. Where gas flows in streams and rings. Where invisible matter quietly shapes the orbits of everything else. Even telescopes on the ground have changed. For a long time, Earth's atmosphere blurred our view, making stars twinkle and smearing out fine detail. Now, with adaptive optics, systems that constantly adjust a mirror to cancel out that blur, big telescopes on high mountains in Chile or Hawaii can reach sharpness that rivals space telescopes. They pick out clusters. They trace narrow dust lanes. They measure the tiny motions of stars around the galaxy. Wide-field cameras have swept across the space around Andromeda and found that it is not alone. Streams of stars arc far from the main disk, like tides pulled away from smaller galaxies that wandered too close and were slowly torn apart. These pale rivers of stars show that Andromeda has grown by eating its neighbors. Its shape, its halo, its history have all been sculpted by these quiet mergers. Modern instruments let astronomers zoom all the way in as well. They catalogue globular clusters, the dense swarms of stars that orbit in the halo. They measure the chemistry of individual stars to tell how old they are and what kind of environment they formed in. They track how stars move through the galaxy to map the hidden distribution of dark matter. The Andromeda we speak of today is not just a blur in the constellation Andromeda. It is a galaxy we have charted from its bright core to its dim outskirts, from its gas to its dust, to its dust to its star clusters. One of the most surprising discoveries is just how vast Andromeda's halo is. Not the bright disk, but the faint cloud of stars and dark matter surrounding it. Observations suggest that this halo stretches across millions of light years, so wide that it may already overlap with the halo of our own Milky Way. That means, in a sense, the outermost reaches of the two galaxies are already touching, long before their disks collide. The meeting of Andromeda and the Milky Way has begun in a way we cannot see with our eyes, but can trace with careful instruments. When you look at a high-resolution image of Andromeda, all of this becomes more than theory. You see the bulge crowded with light. You see the arms sweeping outward, packed with stars. You see dust cutting across them, like dark rivers. Millions upon millions of points fill the frame. It is the same object as the little blur in the sky, but rendered in detail that finally lets your imagination understand why astronomers talk about trillions of suns. These images are not just data. They act like a window. They let us feel the size and richness of our neighboring galaxy in a way that lists of numbers never quite can. And yet, for all of this progress, Andromeda still keeps some of its mystery. Even our best telescopes cannot see everything. There are stars too faint, structures too subtle, histories too tangled to fully unravel. New instruments, like the next generation of space telescopes, will push deeper into dusty star-forming regions, into the population of the oldest stars, into the very outskirts, where the halo fades into the larger cosmic web. Each new view will add another layer, but if you go outside on a clear, dark night and look up, Andromeda will greet you exactly as it greeted Al-Sufi and the unnamed observers before him. A small, pale patch. A faint oval on the edge of what your eyes can catch. All our diagrams and mosaics and multi-wavelength images live in computers and books and memory. The sky itself still offers the same soft blur. Modern telescopes have changed what we know about Andromeda. They have not changed what it feels like to find it with your own eyes. That feeling is as old as human curiosity and as new as the latest image. When you first hear that Andromeda is on its way toward us, it almost sounds like a threat from a science fiction story. You look up and see that faint blur hanging so quietly in the sky, and it feels impossibly far. 2.5 million light-years away, a distance so large that even light takes millions of years to cross it. From where we stand, that sounds like forever. And yet, Andromeda is not frozen in place. It is moving. Not sideways, not drifting away, but coming closer. Slowly, steadily, like two ships far out at sea, whose paths are set long before they ever see each other clearly. Astronomers know this not by watching it creep across the sky with their eyes, but by listening to its light. When we spread Andromeda's light into a spectrum, a rainbow of colors, we can see tiny shifts in those colors. For most galaxies in the universe, the pattern is nudged toward red, showing that they are moving away as space itself expands. Andromeda is different. Its pattern is shifted slightly toward blue. That blue shift means the waves of light are being compressed as the galaxy comes closer to us. It is not part of the general outward flow. It is swimming against it, pulled in by gravity toward the Milky Way. The speed is about 110 kilometers every second in our direction. For us, that sounds fast, faster than anything we could ever travel. But across millions of light years, That speed is more like a slow, patient glide. The meeting is not scheduled for tomorrow, not next year, not even within the entire span of human history so far. The first real encounter will happen in roughly 4 billion years. To imagine what that encounter means, it helps to clear away the picture of two solid objects smashing together. Galaxies are not like rocks, they are mostly empty space. Their stars are so far apart that even when two galaxies overlap, almost all of the stars pass by one another without colliding. The drama of the collision is not in stars crashing head-on, but in gravity reshaping everything. As the galaxies draw near, their gravitational fields begin to tug on each other's shapes, their halos, the vast, faint envelopes of stars and dark matter around them, will overlap first, long before the bright disks ever touch. The stars in each galaxy will feel new pulls, their paths bending and stretching. Some will be slung outward into long streams. Others will be drawn inward toward the growing center. Where the gas clouds meet, the story is less gentle. Gas does not pass through gas the way stars pass through stars. Clouds will collide, compress, and crumple. That compression will trigger bursts of star formation. Whole regions of space will flare, with newborn stars lighting up for the first time. The merger will not be silent. It will glow with fresh starlight. Astronomers have run computer simulations of this future dance. In those models, Andromeda and the Milky Way drift closer over vast stretches of time. On the sky of some distant future world, Andromeda would slowly swell, growing larger over millions of years. It would stop being a little blur and become a great, detailed shape, a galaxy big enough to stretch across a large part of the night. When the two disks first pass through each other, they won't snap together like magnets. They will swing through, continuing onward, but now heavily distorted. Long tidal tails, made of stars pulled away by gravity, will arc out into space like glowing bridges. Over time, the galaxies will curve back toward one another, pull together again. Their motions will tighten into spirals until at last they settle into a single, merged form. The end result will probably not be a neat spiral, like either original galaxy. It is expected to be a large, more rounded galaxy, something like a giant elliptical, a blended system where the original spiral arms have been scrambled and the stars have settled into new orbits within a new hole. Sometimes people call this future galaxy Milkomeda or Milkdromeda, playful names to remind us it is a fusion of two. From Earth's point of view, the collision will be both very dramatic and surprisingly gentle. Dramatic because the sky will change in ways we can barely imagine. The familiar faint band of the Milky Way will be joined by bright, sweeping arcs from Andromeda. Patterns of stars will shift. New streams and clumps of light will appear. Over many generations, the night sky will grow, more crowded, more intricate, like watching a slow, cosmic painting in motion. Gentle, because our solar system is unlikely to crash into another star. Even in the middle of a galactic collision, the spaces between stars are so vast that direct hits are rare. Our Sun and its planets will probably drift into a new orbit within the combined galaxy. Shifted, but not shattered, the real turbulence will belong to the gas. The clouds compressing, the new stars igniting, the bursts of radiation that follow. Deep in the centers of the two galaxies, another meeting will take place. Each has a supermassive black hole at its heart. As the galaxies merge, these black holes will slowly spiral toward one another, losing energy to the surrounding stars and gas. Eventually, they will come close enough to merge into a single, even more massive black hole. That final union will send out ripples in space-time itself, gravitational waves that spread across the universe, like the rings from a stone, dropped into water. No humans will be here to hear that cosmic echo, but somewhere, some distant civilization, or some future instrument might detect the faint shiver and trace it back to the merging of our galaxies. Thinking about all of this bends our sense of time. 4 billion years sits far beyond anything we personally touch. Our written history covers only a few thousand. Our species is only a few 100,000 years old. 4 billion years is the age of the Earth itself, from its birth out of dust and rock to now. To think forward the same distance is to imagine continents drifting, oceans forming and drying, species rising and vanishing, stars being born and dying, all while the galaxies slowly approach. It is not really a prediction of what humans will see. It is more like reading how galaxies live. This is what they do over cosmic time. They move, they meet, they merge, they reshape themselves and go on. There can be a kind of comfort in that. The collision is certain, but it is not a sudden catastrophe. It is a slow, graceful rearrangement. Stars will still shine, planets will still orbit. The galaxies will weave through each other, change shape, and eventually settle together. For any beings alive during the early stages, the sky will be transformed. But the transformation will be a spectacle, not an instant end. Andromeda's slow journey toward us is a quiet reminder that the universe is not static. We sometimes picture space as a fixed backdrop, but nothing in it is truly still. The Milky Way has already swallowed smaller galaxies, their stars now stretched into streams around us. Andromeda has done the same. Their future meeting is just the next step in a long chain of gatherings, a natural part of how structures grow in the universe. Zooming out even more, clusters of galaxies also drift together and merge. Superclusters stretch and shift in the vast cosmic web. Everything is in motion on some scale. We are part of that motion, whether we feel it or not. For us, the word collision suggests something sudden. Cars, rocks, crashes. In galactic terms, a collision is slow and patient. It can last for billions of years. From our brief viewpoint, we live inside a single frame of that slow dance. What seems inevitable to us is just one moment in a much longer story. The thought that the faint blur you can barely see tonight is already on its way toward us adds another layer to its light. The photons reaching you now left Andromeda when it was slightly farther away than it is today. Tonight's light is a message from a slightly earlier step in its journey. Tomorrow's light will come from a point just a little closer. Every clear night, new waves of light arrive, quietly announcing that the galaxy is still moving, still drifting nearer. It is as if the universe is whispering the same reminder again and again. Nothing stays exactly as it is. Change is always underway, even when it happens so slowly that we cannot feel it, even when the horizon of that change lies billions of years ahead. To sit with this is to feel the scale of cosmic patience. Andromeda will not rush its meeting with us. It does not hurry. Its path is already set by gravity. The future galaxy that will form from the merger is already implied in the motions we see now. In that sense, the meeting is not something waiting to start. It has started. We are just watching the earliest, stillness-looking part of the dance. From here, it is natural to wonder about the view. What will it look like when the collision is truly underway? What skies will shine over the worlds that exist then? What shapes will future beings see when they stand under their night and look up at two galaxies melting into one? To picture the future meeting of Andromeda and the Milky Way, you have to let your mind stretch far beyond the timeline we usually live inside. Not years, not centuries, not even the span of human history, but billions of years. About 4 billion years from now, the night sky above Earth, or whatever world our distant descendants might call home, will look nothing like the sky you know. The soft band of the Milky Way will still arch overhead at first, but it will no longer be alone. The faint blur we now strain to see at the edge of vision will grow into one of the brightest, largest structures in the sky. At the beginning, the change will be easy to miss. Long before the galaxies actually touch, Andromeda will simply start to look bigger. Night after night, year after year, it will creep closer by an amount too small for any single person to notice. but over many generations, its oval glow will slowly swell. Eventually, that little patch will rival the moon in size. To the eyes of future observers, it will no longer be a tiny smudge. It will be a vast spiral galaxy hung across the heavens, its arms drawn out in delicate detail, its core shining bright. Imagine looking up and seeing not just the Milky Way, but another full spiral galaxy beside it. Two great star systems painted across the same sky, their shapes clear, their structure visible without any telescope at all. The universe that feels abstract to us now will be written right across the night like a mural. As the galaxies draw closer, gravity will start to twist them out of their neat, spiral forms. Their arms will stretch into long, thin streams called tidal tails. To anyone watching from a planet inside the Milky Way, new arcs of light will appear overhead. Great rivers of stars will curve across the sky, slowly shifting into forms no human eyes have ever seen. The spirals will become distorted, elongated, bent by each other's pull. When the disks finally overlap, the view will grow even more dramatic. The sky will be filled with overlapping clouds of starlight, two galaxies woven together in both structure and sight. The Milky Way will stop being just a single band and become a tangled tapestry of arms and bulges and streams. For those living then, the night will never be truly dark. Wherever they look, stars will crowd the sky, brighter and more numerous than anything we know today. And yet, for all that drama, the experience for individual stars will be surprisingly calm. Even during a galactic collision, stars are so far apart that the chance of two of them actually hitting each other is extremely small. The true action is not in star-to-star impacts, but in orbits changing. Billions of stars will be gently diverted onto new paths, flung into arcs, pulled inward or outward. To a solar system like ours, it might feel, over immense time, like simply drifting into a new neighborhood within the merged galaxy. The gas clouds, however, will not slip by so peacefully. As they crash into one another, they will compress. That compression will trigger intense bursts of star formation. New clusters of stars will ignite in large numbers, many of them hot and massive and bright blue. Huge nebulae, far larger and more luminous than the Orion Nebula we see today, will glow across the sky. Future beings will look up and see not only the old familiar stars, but vast new patches of light, where stars are being born in enormous waves. The two galaxies will not merge in a single pass. They will move through each other, swing apart, then fall back together again. Each encounter will stretch and twist them further, sending out new streams of stars and creating shells and arcs that sweep around the growing central mass. From the perspective of anyone living through these ages, the sky will be in slow, ongoing transformation. Not changing in a way you could notice from one night to the next, but changing enough that each new generation will grow up under a slightly different pattern of light than the one before. After billions of years of this slow dance, the Milky Way and Andromeda will finally settle into a single, blended galaxy. It will likely no longer have the graceful spiral arms that define them now. Instead, it will be a giant, more rounded galaxy. Smooth, full, glowing in all directions with a dense haze of stars. The name Milky Way will no longer describe the shape of the sky for those inside it. They may give their new galaxy another name. Sometimes we call it Milkomeda in our models, a playful hint at the merging of two homes. For whoever looks up in that distant era, the night will be utterly unfamiliar by our standards. But it will carry its own beauty, its own stories. Their constellations will not be ours. Their sky lore will grow from patterns we can only simulate in computers and imagine from a distance. Thinking about that future reminds us that the Andromeda we see now is temporary. The neat spiral, the distinct bulge, the ring of satellites around it. All of these are just one phase in a longer story. The faint blur in our sky is not a permanent decoration. It is a snapshot of a galaxy on its way to becoming something else. Our current view is a single frame in the dance of galaxies, Andromeda's immensity is not only about how wide it is, or how many stars it holds, it is also about its destiny, about the role it will play in reshaping our whole local group of galaxies. The future merger will unfold whether or not Earth is still a safe place. By the time the collision is fully underway, the Sun will be nearing the end of its steady life. It will swell and change, altering or destroying the conditions that make Earth comfortable for us now. Life as we know it may be gone. Other forms of life may have appeared elsewhere. Perhaps descendants of humanity will have moved to new worlds, carrying old memories of how the sky used to look. The story of this merger is not only about physics. It is also about perspective, about our ability, here and now, to imagine a sky no human will ever personally see. Computer simulations let us compress billions of years into a few moments. On a screen, we can watch Andromeda and the Milky Way glide toward each other, distort, fling out streams, and finally settle into one galaxy. It is like watching a time-lapse of the universe rearranging itself. These visualizations remind us that the shapes we admire in telescopes today are not final. Spiral arms, bars, halos. All of these are temporary patterns. Gravity will keep working. Galaxies will keep shifting. The elegant spiral of Andromeda will fade into a new form, not because something has gone wrong, but because change is woven into the nature of the cosmos. Right now, the merger lives only in our predictions and models, a careful forecast written in light and motion. And yet, the fact that we can make such a forecast at all is astonishing. We struggle to predict weather a few weeks ahead. But by measuring Andromeda's light, tracking its motion, and applying the laws of gravity, we can see billions of years into the future of our galaxy. That ability is a sign of how deeply we have begun to understand the universe we live in. So when you look at Andromeda tonight, you are not just seeing what it was millions of years ago. You are also, in a way, seeing what it will help create. Its light carries memory, where it has been, and hints of destiny, where it is going. That faint blur is not a static decoration on the sky. It is a partner in a slow, enormous dance that will one day redraw the heavens. What we imagine for Andromeda and the Milky Way is not unusual. Across the universe, galaxies are constantly merging and reshaping themselves. Small ones are swallowed by larger ones. Large ones collide and form even greater systems. The future here is a local example of a universal story. To know this is to see Andromeda differently, not only as it is, but as it is becoming, a moving piece in a long, ongoing pattern written into cosmic history. When we ask, how big is Andromeda really? It sounds like a question with a clean, simple answer. You can imagine someone replying with a neat line of figures. About 220,000 light-years across. Roughly 1 trillion stars. Perhaps 1.5 trillion times the mass of our Sun. Those numbers are real. They are impressive. But they also hide a deeper problem. Do words like big and size even mean the same thing at this scale as they do in our everyday lives? On human scales, size feels solid and obvious. You know a mountain is larger than a house because you can stand next to both. You know an ocean is larger than a lake because you can travel across them. Watch the shoreline disappear. Even the Earth, with its 40,000 kilometers around, can be held in your mind once you've seen a globe or a photo taken from space. You can imagine flying over it, circling it, measuring it, but a galaxy sits far outside that comfort zone. The units we use to describe it are not kilometers anymore. They are light years. A single light year is already almost beyond intuition. It is the distance light travels in 1 year, nearly 10 trillion kilometers of continuous motion. When we say Andromeda is about 220,000 light-years across, we are stacking hundreds of thousands of those impossible distances side by side. It becomes a number you can say, but not really feel. We try to tame it with images. Imagine a beam of light leaving one edge of the galaxy and racing at the fastest speed allowed by physics. It would have to keep going for 220,000 years just to reach the far side. No pause, no rest. Just pure speed stretched across ages. That is what we mean by size here. It is not something you can walk around. It is something you can only approach through metaphor. And yet, astronomers still need the word size. They need some way to compare one galaxy to another, to say this one is small, this one is average, this one is a giant. Some galaxies are dwarfs, only a few thousand light years from edge to edge. Others are enormous systems stretching more than 500,000 light years. Andromeda sits toward the larger side of that scale, big enough to impress, but not the biggest. Large enough to make our own Milky Way seem modest, but small enough that we know the universe holds even grander structures. But what does it really mean to say one galaxy is twice as wide as another? Does that tell you anything about what it feels like to exist inside it? To be one tiny life form orbiting one tiny star in its disk. In many ways, size in astronomy is a kind of shorthand. A galaxy's diameter tells you how far its bright disk appears to reach, how wide its spiral arms spread, how much space is filled with stars and gas. Its mass tells you how strong its gravity is, how fast stars must move to stay bound, how tightly it can hold on to its satellites. These numbers are not lies, but they are summaries, not stories. When we say Andromeda is this wide or that massive, what we are really saying is that it occupies a certain domain of influence. There is a region of space where its gravity rules, where its stars orbit, where its gas clouds belong. The number we quote for its size is just a label pinned onto that region, a single figure standing in for an entire, complicated reality. It also helps to remember that galaxies do not have crisp edges. There is no sharp line where Andromeda ends and outside begins. Its bright disk fades gradually into a dim halo of stars. That halo then blends into a wider halo of dark matter, invisible but present, stretching far beyond what we can see. Where do you decide to stop the measuring tape? At the visible disk? At the last detectable stars? At the point where its gravity starts to lose its grip to the pull of the surrounding universe? Each choice gives you a different answer. So even the number 220,000 light years is not a sacred truth. It is a convention, a useful cut in a place where nature did not draw a line. When we talk about size, we are also quietly choosing a point of view. Imagine an observer living on a planet inside Andromeda, orbiting some distant sun. To them, the galaxy would feel both huge and strangely unseen. They might see a milky band of stars stretching across their sky, much like we see our own. They might notice dense patches, dark lanes, bright clusters, but they would not see the whole spiral shape laid out like the photos we see. From inside, structure must be inferred, not seen directly. They would have to build instruments, make maps, measure motions, and conclude, eventually. We live inside a spiral galaxy of this approximate size. For them, as for us, the size of the galaxy would be a conclusion, not a daily sensation, something held in thought, not in physical experience. In that sense, size tells you as much about what a curious mind can measure as it does about reality itself. At these scales, maybe size is not the most important thing. Maybe what matters more is structure and relationship. Andromeda is not just a number of light years from one side to the other. It is a spiral, with arms, with a central bulge, with a surrounding halo. It sits in a gravitational dance with the Milky Way. It has its own family of satellite galaxies, its own streams of captured stars, its own record of mergers etched into its outskirts. Its immensity lives not only in how far it stretches, but in how it is connected, how it has grown, how it continues to evolve. Time complicates the idea of size even further. Andromeda is not a frozen object. Its stars orbit. Its arms slowly shift. Its satellites move on long, looping paths. In a few billion years, its ongoing merger with the Milky Way will change its shape completely. If you try to pin its size down as a single, fixed number, you are catching only one frame of something that is constantly in motion. You are freezing a living system into a static label. There is also the question of what we compare it to. Compared to us, Andromeda is beyond enormous. Compared to smaller galaxies, it is a heavyweight. Compared to galaxy clusters and the vast cosmic web, it is just one bright spot among many. Size here is always relative. A galaxy is not big or small in isolation. It is big or small depending on what you place beside it and from where you are looking. To call Andromeda big is to speak from the scale of humans and solar systems. From the scale of superclusters, it is an ordinary citizen. Despite all these complications, our minds keep reaching for numbers. How big? How far? How many? These questions are woven into how we understand the world. Numbers become handles we can grab onto when the thing itself is too large to hold. The answer may never be complete, but the act of asking pulls us closer. So maybe the right way to think about Andromeda's size is this. Size means something, but not everything. It is a doorway, not a full description. When we say Andromeda is about 220,000 light-years wide, we are not claiming to capture its entire reality in a single figure. We are saying, here is something vast. Vaster than your imagination can easily manage, and yet still part of the same universe you live in. The number is both accurate and incomplete, useful and inadequate. A tiny, human attempt to point toward a scale that will always be just beyond our natural reach. And that is part of what makes it worth thinking about at all. On a still, clear night, there is a quiet kind of realization waiting just above you. You're not only standing beneath stars, you're standing beneath galaxies. You're standing beneath galaxies. Our own Milky Way stretches across the darkness like a pale river of light, a soft reminder that we live inside a great city of stars. And just a little aside from that river, faint and easy to overlook, hangs Andromeda. To your eyes, it is almost nothing. A small blur, a pale cloud among sharper, brighter points. But folded inside that blur is something larger than our own galaxy. Almost 1 trillion suns gathered into great spirals and streams. All of it drifting slowly toward us across millions of light years. It's strange to think how much that tiny smudge has carried in human imagination. For a long time, it was only a mystery, a patch of light that people noticed, named and marked on their maps, without really knowing what it was. Then telescopes arrived, and the blur became a revelation. We discovered that the universe was not just our Milky Way. It was full of galaxies, and Andromeda was our nearest great neighbor. Now, with modern instruments, we see it in far more detail. We can trace its arms, dust lanes, and clusters. We can map the halo that stretches far beyond what our eyes can see. We can pick out the small companion galaxies that orbit it. We can weigh it, measure how wide it is, and track how it moves. We can even predict that one day, far in the future, it will merge with our own galaxy. But when you are actually standing under the night sky, none of those details are required. The numbers can fall away. The experience of simply looking up is enough. You might know that it is huge. You might know that it holds more stars than you could ever count. You might know that it is gliding gently toward us over billions of years. Yet, in the moment of seeing, it is just a soft glow. A quiet reminder that the universe contains more than your eyes can truly take in. It doesn't demand that you solve it. It simply invites you to pause, to breathe, to let the sheer scale of it sit with you for a while. When you fall asleep beneath that kind of sky, you can carry that feeling inward. You can let your thoughts drift outward to the scale of galaxies. You can picture their arms slowly sweeping through space, stars circling their centers in vast, unhurried orbits. Invisible black holes sitting deep in their cores, holding the inner regions together with gravity alone. You can imagine Andromeda as it is tonight, as it was when the light, now reaching you, first set out, as it will be when it finally merges with the Milky Way. Your mind cannot hold all of that at once, and it doesn't have to. It can wander gently between the pieces, from stars to dust to halos to mergers, resting in the rhythm of that immensity. There is a kind of comfort hidden in those scales. Galaxies move on time frames so long that your own worries begin to soften against them. The small stresses of today feel sharp and urgent. They press on your thoughts and crowd your attention, but compared to a billion-year dance of two galaxies, even the heaviest feeling becomes brief. That doesn't make what you feel unimportant. Your life still matters deeply, especially to you and to the people around you. It simply gives you a new frame to place it in, a way to remember that this moment, with all its weight, is one tiny part of a much larger story. To sleep under Andromeda is to let that story soften the edges of your thoughts, to remember that you live inside a universe that stretches far beyond this day, this week, this year, that you are part of a cosmos that is ancient and ongoing, and you are allowed to rest inside it. Andromeda is not just out there in the sky, it is in here as well, in the atoms that make up your body, the carbon in your cells, the oxygen in your lungs, the iron in your blood. Those elements were forged long ago in stars very much like the ones that fill Andromeda. You are built from star material, recycled and reassembled over billions of years, shaped by the same physics, carried through the same cycles. Thinking of that as you drift towards sleep can make you feel less separate. You are not just a small person staring at a distant galaxy. You and that galaxy are made of the same kind of stuff. You are part of the same unfolding universe that created those spirals of light. The galaxy will go on long after tonight. Long after you close your eyes. Long after you wake up tomorrow. Long after our species has come and gone, its stars will continue to rise, burn, and fade. Its arms will slowly change. Its future merger with the Milky Way will reshape it into something new. But for now, in this moment, its light has arrived here.
Photons that set out millions of years ago are ending their long journey in your eyes.
That alone is astonishing. You become part of its story simply by seeing it, by knowing it exists, by letting the thought of it rest in your mind as your body relaxes. So as you lie back and let your breathing slow, you can picture that faint glow above you. You can imagine its arms stretching wide through space. Its countless stars, each with its own quiet story. Its future, immense and calm, unfolding over eons. Let it remind you that you are small, but never truly alone. That your time is brief, but held inside something enduring. That the universe is vast, and yet you are capable of feeling that vastness, of thinking about it, of finding peace inside it. As sleep comes closer, you can carry that glow with you. The glow of a trillion distant suns. The glow of a neighboring galaxy drifting slowly toward our own. The glow of the universe itself, mirrored in your quiet thoughts. It is not just a patch of light in the sky. It can be a companion in the night. A gentle reminder that even in darkness, there is always more beyond what you can see. Always something greater holding you. Always a reason to look up, if only in memory, as you drift into dreams. Thank you for spending this time beneath the stars. If these thoughts have brought you calm, you're always welcome to return and let the universe keep you company again. For now, may your night be peaceful, may your thoughts grow light, and may sleep arrive softly, carrying you gently into dreams.